Hello there and welcome to Life Beyond Seen, where curiosity settles in quietly, science slows its pace a little, and complex ideas are explored in a way that lets the mind wander without getting lost. Tonight, we're turning our attention toward a place that sounds simple at first glance, a lake, just a body of water on a map. But this one refuses to stay simple for very long, because the more closely people study Lake Baikal, the clearer it becomes that it isn't a place we fully explore, not in the way we usually mean when we talk about exploration. Lake Baikal sits in Siberia, vast, cold, and quietly persistent. It holds records: oldest lake on Earth, deepest freshwater lake, largest reserve of unfrozen freshwater by volume. Those facts alone already stretch the imagination a bit, yet they still don't quite explain why scientists, divers, engineers, and researchers keep returning to it with the same feeling, that they are only scratching the surface, even when they go far below that surface. If you pause for a moment, it is interesting to consider where you're listening from right now. Different cities, different countries, maybe a late evening room, maybe an early morning commute, maybe headphones under a blanket while everything else has gone quiet. And wherever that happens to be, the idea that somewhere on this planet there exists a place so studied, yet still so partially understood, tends to spark a certain kind of curiosity. It's the sort that doesn't rush, it just sits there patiently. If this kind of slow exploration feels calming or simply interesting, a small like or subscription helps this calm little corner reach others who might appreciate the same pace. No pressure, of course, just a gentle reminder before we drift deeper into the story. Now, when most people imagine exploration, they picture progress that feels steady and predictable. You send a satellite into orbit, you map coastlines, you drill ice cores, you catalogue species. Eventually gaps close, unknowns shrink, knowledge grows. That is generally how the story goes. Lake Baikal complicates that narrative. The more tools we bring, the more measurements we collect, the more data we store, the clearer it becomes that certain limits remain stubbornly in place. Some of those limits are physical, some are technological, some are environmental, and some are simply about scale. Baikal is enormous in ways that do not translate well into everyday experience. Standing on its shore, it often looks more like a sea than a lake. Horizons stretch, weather changes quickly. Depth readings begin to resemble ocean figures rather than inland ones. That scale alone already slows exploration down, but scale is only one part of the puzzle. Another factor is age. Lake Baikal is estimated to be around 25 million years old. Most lakes, geologically speaking, are temporary. They fill with sediment, dry out, freeze over permanently, or transform into something else. Baikal has persisted through ice ages, continental shifts, and climate cycles that erased many other lakes entirely. That longevity means its ecosystems developed in relative isolation for a very long time. Species evolved there that exist nowhere else. Biological systems formed that behave differently from what researchers expect when they arrive with assumptions built from studying younger lakes. And then there is depth. At over 1,600 meters, Baikal reaches farther down than many marine environments close to shore. Fresh water at those depths behaves differently than seawater. Pressure increases steadily. Light fades quickly. Temperature remains consistently low. Equipment that works well in oceans sometimes struggles here because design assumptions shift when salt content disappears and extreme cold dominates. Even getting to the lake presents challenges. Siberia is not exactly around the corner for most research institutions. Logistics require planning that often spans years. Transporting submersibles, maintaining research vessels in freezing conditions, coordinating international scientific teams, and securing funding all add layers of complexity before a single measurement even begins. Winter adds its own chapter to the story, though calling it a chapter makes it sound orderly, which Baikal rarely is. The lake freezes over with ice thick enough to support vehicles, yet that same ice moves, cracks, shifts, and produces pressure ridges that can appear without much warning. Researchers working on the ice must constantly reassess safety conditions. Beneath the ice, water remains active. Currents continue. Life continues. The surface calm does not always reflect what is happening below. Summer removes the ice but introduces storms. Winds funnel through surrounding mountain ranges. Waves build quickly. Visibility changes. Equipment deployment windows narrow. Sometimes a carefully planned expedition becomes a waiting exercise. Crews watching weather forecasts while expensive instruments sit idle on deck. Despite all that, exploration continues. Submersibles descend. Sonar mapping progresses. Biological surveys catalogue organisms. Sediment cores reveal climate history stretching back millions of years. And yet conversations with researchers often circle back to the same theme. They describe progress, yes, but also a persistent sense that Baikal keeps certain things just out of reach. Part of that comes from what the lake contains biologically. More than half of its species are endemic, meaning they evolved there and nowhere else. Some are microscopic organisms adapted to extreme cold and pressure. Others, like the Baikal seal, exist in ways that still puzzle scientists. How exactly a seal species came to live in an inland freshwater lake remains debated. Migration routes during ancient glacial periods provide some clues, but not all. When new species are discovered, which still happens regularly, they tend to raise further questions rather than closing old ones. Food chains behave differently in ultra-cold freshwater. Reproductive cycles adapt to unusual seasonal light patterns. Microbial communities and deep sediments interact chemically with the water column in ways researchers are still mapping. Technology, impressive as it has become, encounters limitations here too. Autonomous underwater vehicles function well in many ocean settings, but Baikal's depth combined with low temperatures affects battery efficiency, sensor calibration, and communication reliability. Fiber optic tether systems help, yet they restrict range and maneuverability. Every engineering solution seems to trade one limitation for another. Mapping the lake floor illustrates this clearly. Large portions have been surveyed using sonar, producing increasingly detailed topographic models. But mapped does not mean fully understood. Sediment layers shift. Hydrothermal vents exist in certain deep zones, altering local chemistry. Geological activity linked to the rift valley underlying Baikal continues slowly, meaning the lake is still evolving. That geological aspect is often overlooked. Baikal sits along a continental rift, a place where Earth's crust is gradually pulling apart. Very gradually by human standards, but actively nonetheless. This contributes to depth, seismic activity, and ongoing changes to basin shape. Studying an environment that is still forming adds complexity, because baseline conditions are not fixed. Water clarity presents an interesting contrast. Near the surface, Baikal can be exceptionally clear. Divers sometimes report visibility exceeding 40 meters. That sounds ideal for exploration, but clarity drops with depth as light fades and particulate matter increases. Past certain levels, artificial lighting becomes necessary, which then introduces its own observational biases. Creatures react differently to light. Cameras capture only what illumination allows. Temperature stability also plays a role. Deep water remains just above freezing year-round. Machinery operating in those conditions requires insulation, lubrication suited to cold environments, and materials resistant to brittleness. Maintenance becomes more demanding. Retrieval for repairs can take months depending on seasonal access. Human endurance matters too. Cold environments tax concentration. Extended research stays in remote Siberian locations challenge logistics, morale, and physical comfort. Exploration is not just instruments descending into water. It is people coordinating complex operations in demanding surroundings. Cultural perspectives surrounding the lake add another layer that researchers increasingly acknowledge. For many local communities, Baikal is not merely a geographic feature. It holds spiritual, historical, and cultural significance. Respectful research involves collaboration, consultation, and awareness that scientific curiosity intersects with long-standing human relationships to the landscape. Environmental protection concerns further shape exploration. Baikal contains roughly 20% of the world's unfrozen freshwater. Pollution risks carry global implications. Industrial activity around the lake has decreased compared to past decades, but monitoring continues. Research missions must balance discovery with preservation. All of these factors combine into a situation where exploration happens continuously, yet completeness remains elusive. Data accumulates, publications expand, conferences discuss findings. Still, when someone asks whether Lake Baikal is fully explored, the answer tends to be cautious. Not quite, not yet, possibly not ever in the absolute sense. And that realization shifts the conversation slightly. Exploration stops being a race toward a finish line and becomes an ongoing relationship with a place that resists total familiarity. Scientists return not because they expect final answers soon, but because each visit adds another piece to a very large, very complex picture. That picture includes chemistry as well. Baikal's water composition differs subtly from many other freshwater systems. Oxygen penetrates to great depths, supporting life where many lakes would become anoxic. Nutrient cycles behave differently. Winter mixing patterns redistribute dissolved gases. Long-term monitoring reveals trends linked to climate change, some gradual, some unexpectedly rapid. Climate itself introduces uncertainty. Ice cover duration has shifted slightly over recent decades. Surface temperatures show small but measurable increases. Biological responses follow. Some endemic species display resilience, others show sensitivity. Understanding those dynamics requires consistent observation over long time scales, which means exploration is inherently ongoing. When discussions turn to whether we can't truly explore Baikal, the phrase does not imply failure. It reflects recognition of limits. Physical limits, technological limits, ecological limits, and even conceptual limits. Sometimes understanding grows not by conquering a place completely, but by learning how to observe it responsibly over time. That perspective starts to make more sense the longer one looks at Baikal. It's not hiding intentionally. It simply operates on scales and conditions that do not align neatly with human expectations of thorough exploration. Depth, age, cold, biology, geology, logistics, culture, and environmental stewardship all intersect there. And once those factors begin to line up in your mind, the lake starts to feel less like an unsolved puzzle and more like an ongoing conversation between nature and observation, one where patience tends to produce better insights than urgency. From that angle, the question shifts slightly away from whether we will ever finish exploring it, and toward how exploration itself adapts when the subject refuses to be neatly completed, which naturally leads further into the specific environmental conditions that make even routine research missions there quite different from similar work in other freshwater lakes. When most people hear the word lake, the picture that forms is usually manageable in scale. A calm stretch of water, maybe a shoreline with trees, perhaps a small boat moving slowly across the surface. Lakes tend to feel contained. You can often see the other side. You can imagine walking around them, mapping them, understanding them without too much difficulty. That expectation quietly shapes how we approach any inland body of water, even before we know anything about it. Lake Baikal gently but firmly disrupts that expectation almost immediately. Standing on its shore does not always produce the familiar sense of enclosure people associate with lakes. The horizon stretches far enough that the opposite side often disappears entirely. Weather rolls in like it does overseas. Winds gather strength without much warning. The scale alters perception before any scientific measurement even begins. This shift in perception matters because exploration is influenced by how humans categorize environments. Oceans get one set of assumptions, lakes get another. Baikal sits awkwardly between those mental boxes. Officially it is a lake, of course, freshwater, inland, geographically bounded. Yet many of its characteristics resemble oceanic conditions closely enough that traditional lake research models sometimes require adjustment. Depth is usually the first statistic mentioned, and understandably so. More than 1,600 meters at its deepest point places Baikal far beyond typical lake depth ranges. Many lakes around the world average tens of meters deep. A few reach a couple hundred. Baikal descends into territory where pressure, temperature, gradients, and light penetration begin behaving less like typical freshwater systems and more like certain marine basins. Pressure at those depths affects both biological organisms and research equipment. Materials that function reliably in shallower freshwater conditions experience stress differently here. Seals must be reinforced. Sensors require recalibration. Submersibles designed for ocean research sometimes adapt better than those built strictly for lakes, yet freshwater chemistry introduces its own engineering considerations, especially concerning buoyancy and corrosion. Then there is the volume of water. Baikal holds about 20% of the planet's unfrozen freshwater. That figure is often repeated, yet it is worth slowing down long enough to consider what it implies operationally. Sampling even a tiny fraction of that volume thoroughly is an enormous task. Water chemistry can vary by depth, location, season, and biological activity. Long-term monitoring becomes essential, and long-term monitoring requires consistent access, funding stability, and technological reliability. Surface conditions complicate matters further. Winds sweeping across Siberia can generate waves substantial enough to challenge research vessels. Unlike oceans, where wave forecasting infrastructure is extensive and continuously updated, inland systems sometimes lack the same density of monitoring stations. Baikal has improved significantly in that regard over recent decades, yet unpredictability remains part of daily operations. Seasonal ice cover introduces another distinctive factor. During winter, large portions of the lake freeze solid. Ice thickness can exceed a meter in places, strong enough to support vehicles and temporary research installations. At first glance, that might seem advantageous. A stable platform directly above study sites sounds ideal. In practice, the ice moves, cracks, and produces pressure ridges that shift unpredictably. Acoustic monitoring becomes tricky when ice flexes. Drilling access holes requires constant safety reassessment. Equipment deployment must account for ice drift. Under the ice, conditions differ again. Light penetration drops dramatically. Temperature stabilizes near freezing. Some biological activity slows while other processes continue steadily. Researchers working beneath ice often describe a kind of muted environment where sound travels differently and visual cues diminish quickly. All of this contributes to the sense that Baikal resists simple classification. It is not just large. It behaves in ways that challenge assumptions about inland freshwater systems. Scientists who arrive expecting a typical lake sometimes leave adjusting their terminology slightly, referring to Baikal as an inland sea in casual conversation, even while acknowledging the technical definition remains lake. Geologically, the lake sits in an active continental rift zone. Earth's crust is slowly pulling apart beneath it. That process formed the basin millions of years ago and continues subtly today. Seismic activity occurs periodically. Most events are minor, but their cumulative effect influences sediment distribution, hydrothermal vent formation, and long-term basin evolution. Hydrothermal vents in a freshwater lake sound unusual because they are more commonly associated with oceanic mid-ocean ridges. Yet Baikal hosts several. These vents release mineral-rich water from beneath the lake floor, altering local chemistry and supporting specialized microbial communities. Studying them requires deep submersible access and careful chemical analysis. The environments are fragile, and disturbance risks altering delicate biological balances. Sediment layers on the lake floor provide another record stretching back millions of years. Core samples extracted from those sediments help reconstruct climate history, volcanic activity, regional vegetation patterns, and even atmospheric composition changes over geological timescales. Extracting cores from extreme depths demands precision drilling equipment capable of operating reliably under pressure and cold conditions, often far from immediate technical support. Biologically, Baikal stands out because of its endemic species. Over half the organisms identified there exist nowhere else. That includes fish, crustaceans, microorganisms, and the well-known Baikal seal. Evolution in relative isolation allowed unique adaptations to develop. Some species tolerate cold temperatures with biochemical strategies not commonly observed elsewhere. Others occupy ecological niches that do not have direct parallels in other freshwater systems. Understanding these organisms involves repeated sampling across seasons and depths. Population dynamics shift with subtle environmental changes. Climate trends, nutrient inputs, and water clarity all influence ecological balance. Each sampling expedition adds data, but also reveals new variables requiring further investigation. Water clarity itself is often highlighted. Near-surface visibility can be remarkable, sometimes exceeding 40 meters. That clarity stems partly from low nutrient levels and specialized zooplankton that filter particulate matter efficiently. However, clarity varies seasonally. Algal blooms, sediment disturbance, and temperature changes alter visibility. Deeper layers remain dark regardless of surface clarity, requiring artificial lighting for observation. Artificial lighting introduces observational complications. Many deepwater organisms respond to light exposure, altering behavior. Cameras capture what illumination reveals, but illumination itself can influence what appears. Researchers factor this into study design, yet it remains a reminder that observation always interacts with environment. Chemical composition of Baikal's water differs subtly from other freshwater bodies. Oxygen penetrates unusually deep, supporting aerobic life far below levels typical in many lakes. Nutrient concentrations remain relatively low, influencing productivity patterns. Understanding these chemical balances helps explain biological diversity, but also complicates predictive modelling. Logistically, the lake's remote location continues to shape exploration. Transportation infrastructure has improved compared to past decades, yet moving heavy scientific equipment into Siberia remains a significant undertaking. Seasonal access windows, customs procedures, funding cycles, and international collaboration logistics all influence research scheduling. Research stations around Baikal vary from permanent institutes to temporary field camps. Each supports specific projects. Maintaining continuity across projects requires coordination among institutions, sometimes across countries. Data sharing agreements, standardized methodologies, and long-term funding commitments all contribute to cumulative understanding. Human history around Baikal stretches back thousands of years. Indigenous communities developed cultural practices closely tied to the lake. Fishing traditions, seasonal migrations, and spiritual perspectives form part of the human relationship with Baikal. Modern scientific work increasingly incorporates dialogue with these communities, recognizing that local knowledge often complements formal research. Environmental stewardship concerns have grown as awareness of Baikal's global freshwater importance increases. Industrial pollution during the 20th century raised alarms. Some sources have been reduced or eliminated, but monitoring continues. Even small contamination events attract attention because of the lake's ecological significance. Tourism introduces additional complexity. Visitors drawn by the lake's reputation bring economic benefits to surrounding regions, yet increased human presence requires careful management. Waste disposal, shoreline development, and transportation infrastructure all intersect with conservation priorities. Climate change remains an ongoing research focus. Surface temperature trends, ice cover duration, precipitation patterns, and watershed inputs all show subtle shifts. Predicting long-term effects requires extensive data sets spanning decades. That reinforces the idea that exploration here is not a one-time achievement, but a sustained observational effort. Technological advances continue improving measurement capabilities. Autonomous underwater vehicles grow more capable. Remote sensing satellites provide higher resolution imagery. Genetic sequencing reveals microbial diversity previously undetectable. Each advancement opens new investigative pathways, yet also expands the list of questions. There is a tendency in human thinking to equate mapping with understanding. Once a place appears on a map in detail, it feels known. Baikal gently resists that assumption. Bathymetric maps exist. Geological surveys exist. Biological catalogues expand annually. Still, interactions among those elements remain complex enough that complete understanding stays just beyond immediate reach. That does not diminish the value of exploration. It reframes it slightly. Researchers approach Baikal increasingly as a dynamic system requiring continuous observation, rather than a static feature awaiting final description. This perspective encourages caution, patience, and collaboration across disciplines. Oceanographers, limnologists, geologists, biologists, chemists, climatologists, and engineers all contribute pieces. Integrating those pieces requires communication structures capable of handling large data sets and varied methodologies. Conferences, joint expeditions, and shared digital platforms facilitate that integration. Public perception of Baikal often centers on its superlatives: deepest, oldest, largest freshwater reserve. Those descriptors attract attention, but they only hint at the complexity beneath. Appreciating why the lake resists complete exploration involves looking beyond records toward processes, interactions, and ongoing change. Even simple activities like measuring water temperature profiles require precision. Sensors must be calibrated carefully. Deployment depth must be accurate. Retrieval schedules must align with weather windows. Data analysis must account for instrument drift and environmental variability. Similarly, biological sampling involves ethical considerations. Removing organisms for study affects ecosystems. Non-invasive observation techniques gain popularity, yet they also have limits. Balancing knowledge acquisition with conservation remains an active discussion within the research community. Hydrological inputs from rivers feeding Baikal add further variables. Sediment load, nutrient influx, and seasonal flow changes influence water chemistry and biological productivity. Monitoring tributaries becomes part of lake exploration, even though they lie beyond the main basin. Outflow through the Angara River connects Baikal to larger watershed systems. Downstream ecological effects tie the lake to broader regional environmental dynamics. Exploration therefore extends conceptually beyond the lake's immediate boundaries. All of these layers reinforce the idea that Baikal is not simply a large lake awaiting final mapping. It functions as an interconnected system spanning geology, biology, chemistry, climate, and human activity. Each research effort illuminates one aspect while revealing connections to others. Over time, this accumulation of insights changes how scientists describe their work there. Instead of talking about finishing exploration, they talk about deepening understanding, refining models, and improving monitoring techniques. The language shifts subtly but meaningfully, and once that shift settles in, the phrase, "a lake that isn't just a lake," starts to feel less like a poetic exaggeration and more like a practical observation grounded in decades of research experience, which naturally leads toward considering how the lake formed in the first place, because understanding its origin begins to explain why its present-day characteristics diverge so strongly from what most lakes typically display. If you look at a global map and trace your finger across eastern Siberia, Lake Baikal appears as a long, narrow crescent. From space it looks almost like a wound cut into the continent. That shape is not accidental. It is the surface expression of something happening far beneath it, something slow, powerful, and still unfinished. Lake Baikal exists because the Earth's crust is pulling apart at that location. It sits inside what geologists call a continental rift zone. In simple terms, a rift is a place where tectonic forces are stretching the crust instead of compressing it. Over millions of years, that stretching causes the land to thin, crack, and sink. The result is a deep basin, one that can eventually fill with water. This process is not dramatic in the way volcanic eruptions or earthquakes are dramatic. It does not announce itself loudly on human timescales. It moves millimeters per year. Yet given enough time, millimeters accumulate into kilometers. Baikal's basin has been forming for roughly 25 million years. That makes it the oldest existing freshwater lake on Earth. Most lakes are temporary features in geological terms. Glacial lakes form and vanish within tens of thousands of years. Tectonic lakes sometimes last longer, but even they usually fill with sediment, dry out, or transform into marshland. Baikal did not follow that typical life cycle. Instead of gradually filling and disappearing, it continued to deepen as the rift widened. The depth we measure today, more than 1,600 meters, represents only the water column. Beneath that water lies an additional several kilometers of sediment accumulated over millions of years. Under that sediment, the crust continues to thin and stretch. In total, the rift structure beneath Baikal extends far deeper than the visible lake suggests. Calling it the deepest scar on Earth is not dramatic language for effect. It is a geological description. The lake marks a zone where the planet's surface is literally splitting apart. If the rifting process continues for tens of millions more years, this region could eventually resemble an ocean basin. Some scientists compare Baikal's rift to an early stage of the process that formed the Atlantic Ocean. For exploration, this geological context changes everything. Studying Baikal is not just studying a body of water, it is studying an active tectonic system. The lake floor is not static. Fault lines cut through sediment layers. Seismic activity occurs regularly, though often at low magnitudes. Hydrothermal vents release mineral-rich fluids from below. The basin continues to evolve. Seismic monitoring stations around Baikal record hundreds of small earthquakes each year. Most are too minor to be felt by people living nearby, but their cumulative effect reveals that the crust is under tension. Every tremor subtly reshapes stress patterns underground. Over geological time, those stresses alter basin depth and shoreline configuration. Sediment cores extracted from the lake floor provide a layered history of these changes. Each layer corresponds to a different period in the lake's development. Volcanic ash deposits mark distant eruptions. Fossilized pollen grains reveal shifts in regional vegetation. Chemical signatures indicate temperature changes over glacial and interglacial cycles. Because Baikal has existed continuously for so long, its sediment record extends far beyond what most lakes can offer. That record makes it a valuable archive of climate history. Scientists drill deep cores to reconstruct past atmospheric conditions and ecological responses. These cores sometimes reach several hundred meters into the sediment, representing millions of years of accumulated material. Drilling at such depths in cold freshwater conditions is technically demanding. Equipment must remain stable under pressure and low temperature. Core samples must be retrieved intact to preserve layering. Contamination risks must be minimized. Each drilling campaign requires careful planning and often international collaboration. The rift structure also influences water chemistry. Hydrothermal vents located in deeper zones release minerals and heat into surrounding water. Unlike ocean vents, which are typically associated with extreme temperatures, Baikal's vents are relatively moderate. Still, they alter local chemical conditions and support specialized microbial communities. These microbial communities are of particular interest because they thrive in environments shaped by geological activity, rather than sunlight-driven processes. Studying them helps scientists understand how life adapts to chemically distinct habitats. It also informs hypotheses about life in extreme environments elsewhere, including potentially beneath icy moons in our solar system. Exploring hydrothermal zones in Baikal requires deep submersibles capable of withstanding pressure and navigating complex terrain. Sediment plumes can reduce visibility. Vent structures may be fragile. Sampling equipment must be precise to avoid disturbing surrounding ecosystems unnecessarily. The basin's ongoing widening also affects shoreline stability. Over long periods, the lake expands slightly as the rift continues to pull apart. That expansion is slow enough that it does not dramatically reshape maps within a human lifetime, but measurable geodetic data confirm movement. GPS stations placed around the region detect subtle shifts each year. Understanding these shifts matters for infrastructure planning as well as scientific modelling. Towns and transportation networks around the lake depend on accurate geological assessments. Research into tectonic activity therefore intersects with civil engineering and hazard preparedness. The surrounding mountain ranges provide further clues to the rift's dynamics. They rise steeply from the lake's edge, evidence of crustal movement. As the basin sinks, adjacent blocks of crust can uplift. This creates dramatic elevation differences between shoreline and surrounding terrain. From an exploration standpoint, steep underwater slopes complicate mapping. Sonar surveys must account for sharp gradients. Sediment distribution varies depending on slope angle and seismic disturbance. Some areas accumulate thick sediment layers, while others remain relatively exposed rock. The thickness of sediment beneath Baikal is extraordinary. In some places it exceeds 7 kilometers. That means the total depth of the rift system, counting water plus sediment, rivals some oceanic trenches. However, unlike ocean trenches formed by subduction zones, Baikal's depth results from crustal stretching. This distinction influences how scientists interpret the lake's long-term future. Subduction zones eventually recycle crust back into the mantle. Rift zones, if they continue widening, may evolve into new ocean basins. Baikal is sometimes described as a potential embryonic ocean, though that transformation would require tens of millions of years. Even if it never reaches that stage, the fact that it remains tectonically active ensures continued geological change. That dynamic quality means exploration cannot assume static conditions. Maps created today may require revision centuries from now as sediment accumulates and basin geometry shifts. Temperature gradients within the lake reflect its depth and geological setting. Deep water remains near freezing year-round, insulated by upper layers and influenced by basin shape. Seasonal turnover events mix surface and deeper waters differently compared to shallower lakes. Modelling these mixing patterns requires understanding basin morphology shaped by tectonics. Seismic activity occasionally triggers underwater landslides. When sediment shifts rapidly down steep slopes, it can generate localized turbidity currents. These events redistribute material across the lake floor. Evidence of past underwater landslides appears in sediment cores and sonar imagery. Such processes remind researchers that Baikal's depths are not quiet archives untouched by motion. They are part of a living geological system. Each tremor, each slope failure, adds complexity to sediment layering and chemical gradients. Exploring these processes often involves deploying arrays of instruments on the lake floor. These instruments monitor pressure changes, temperature fluctuations, and seismic vibrations over extended periods. Retrieving them requires precision navigation and favourable weather conditions. Winter ice cover sometimes assists in deploying certain types of equipment because stable ice platforms allow drilling directly above specific coordinates. However, as mentioned earlier, ice movement introduces risk. Planning must incorporate detailed ice monitoring. The rift environment also influences groundwater interaction. Subsurface flows connect with the lake at various points, altering chemical composition locally. Identifying these inflows requires geochemical tracing and sometimes isotopic analysis. From a broader perspective, Baikal serves as a natural laboratory for studying continental rifting. Comparing it with other rift systems such as the East African Rift helps geologists understand similarities and differences in tectonic evolution. Baikal's cold climate contrasts with tropical rift environments, offering unique insights into how climate interacts with tectonics. All of these geological factors reinforce the idea that exploring Baikal is not simply a matter of measuring water depth and cataloguing fish species. It involves engaging with an active tectonic scar that continues to reshape itself slowly. The word scar carries certain connotations, but in geology it describes structural weakness and transformation. A scar marks where forces have altered the surface. In Baikal's case, that alteration opened a basin deep enough to hold a fifth of the planet's unfrozen freshwater. When researchers descend into Baikal's depths, they are moving into a space created by millions of years of tectonic stretching. The cold water filling that basin conceals an ongoing geological story. Instruments capture pieces of that story, yet no single expedition captures it entirely. Seismic reflection surveys provide images of sediment layers beneath the lake floor. These images reveal fault lines and folded strata. Interpreting them requires integrating geophysical data with drilling results. Each method confirms and refines the other. The basin's asymmetry adds further complexity. One side may descend more steeply than the other, depending on fault orientation. Sediment accumulation patterns differ accordingly. Currents interacting with basin shape influence nutrient transport and biological distribution. Long-term tectonic activity also shapes habitat diversity. Varied depths and sediment types create ecological niches. Endemic species evolved partly in response to these geological structures. In that sense, the deepest scar does not just influence physical geography, it shapes biological evolution. As researchers continue mapping and drilling, new details emerge. Yet each detail fits into a framework that remains open-ended. The rift is not finished forming, the lake is not finished evolving. Exploration here means observing a process still underway, and once that realization settles in, it becomes clear why Baikal resists being categorized as fully explored. You cannot complete the study of a system that continues to change. You can measure, model, and monitor, but you're always documenting a moment within a longer unfolding sequence. Understanding the tectonic origin of Baikal also prepares us to consider the sheer quantity of water occupying that basin, because the depth carved by rifting created capacity on a scale that shifts the conversation from geology alone toward the immense freshwater reserve that now fills this continental fracture. When people first hear that Lake Baikal holds about 20% of the world's unfrozen freshwater, the statistic often sounds impressive but abstract. Percentages can do that. They communicate scale without always helping the imagination catch up. 20% of something enormous still feels like a number floating somewhere beyond everyday experience. But if you slow down with it for a moment, the implications begin to unfold in a more concrete way. Lake Baikal contains roughly 23,600 cubic kilometers of fresh water. That is not surface area, that is actual water volume, the three-dimensional measure of what fills the basin. If every river on Earth suddenly stopped flowing into oceans and instead fed a single inland reservoir, it would take a very long time to accumulate that much water. Some estimates suggest that all the rivers of the world combined would need nearly a year to match Baikal's volume. That comparison helps illustrate why scientists treat the lake not just as a regional feature, but as a globally significant freshwater reserve. Freshwater itself is already relatively scarce when viewed from a planetary perspective. Most of Earth's water is saltwater. Of the freshwater portion, a large fraction is locked in glaciers or polar ice caps. Some lies deep underground in aquifers. The accessible freshwater people rely on for drinking, agriculture and ecosystems represents only a small slice of the total. Baikal's share of that accessible portion is therefore disproportionately large. This sheer volume shapes nearly every aspect of exploration. Sampling such a massive body of water thoroughly is not simply a matter of sending a few research vessels out for seasonal surveys. Spatial variability alone demands extensive monitoring networks. Temperature, oxygen concentration, nutrient levels and biological activity can differ significantly between regions separated by hundreds of kilometres. The lake stretches about 636 kilometres from north to south. That length alone rivals some coastal marine systems. Its width varies, but in places exceeds 70 kilometres. Combined with its depth, those dimensions produce an inland water body whose hydrodynamics behave more like a small sea than a typical lake. Currents within Baikal are complex. Wind-driven surface currents interact with deeper density-driven flows. Seasonal temperature changes influence stratification patterns. Winter ice cover alters wind influence but introduces thermal stability near the surface. Modelling these currents requires long-term data collection and sophisticated computational analysis. Water turnover in Baikal happens slowly compared with many lakes. Because of its depth and volume, the time required for complete water renewal can extend over centuries. That means any chemical or biological changes introduced into the system persist longer than they would in smaller lakes with faster flushing rates. From an environmental standpoint, that slow turnover has both advantages and risks. On the positive side, it contributes to the lake's remarkable clarity and stable ecological conditions. On the risk side, pollutants introduced into the system may remain detectable for extended periods. This reality influences conservation policy and industrial regulation in surrounding regions. Understanding the full extent of the lake's water also involves studying its inputs and outputs. More than 300 rivers and streams feed Baikal. These tributaries carry sediment, nutrients, organic matter, and occasionally contaminants from surrounding landscapes. Monitoring inflow conditions becomes part of understanding the lake itself. The primary outflow, the Angara River, carries water away from Baikal toward the Arctic Ocean basin. That outflow regulates lake level within certain bounds. Hydroelectric dams downstream influence flow dynamics, adding another layer of human interaction with the lake's hydrology. Seasonal fluctuations in water level occur, but Baikal's enormous volume dampens rapid changes. Compared with smaller lakes that may rise or fall dramatically with seasonal rainfall, Baikal's level shifts more gradually. Still, long-term climate trends can influence these patterns, making continuous measurement important. Water temperature distribution across such a large volume also presents challenges. Surface layers respond relatively quickly to seasonal air temperature changes. Deeper layers remain consistently cold, hovering just above freezing. That thermal stability influences oxygen solubility, nutrient cycling, and biological activity at depth. Unlike many deep lakes that develop oxygen-depleted bottom waters, Baikal maintains oxygen presence throughout much of its depth. This unusual feature supports life in deep zones where other lakes might become inhospitable. Researchers study mixing mechanisms responsible for maintaining this oxygen distribution. Wind patterns play a role in vertical mixing. Strong seasonal winds can drive surface water downward in certain areas, promoting oxygen transport. Basin shape and tectonic features influence how effectively that mixing penetrates deeper layers. Studying these mixing processes requires coordinated measurement campaigns. Temperature sensors, oxygen probes, current meters, and chemical sampling all contribute data. Instruments often remain deployed for extended periods, collecting continuous records that researchers later analyze for trends. Water clarity, frequently noted by visitors, relates partly to the lake's nutrient balance. Low nutrient concentrations limit large-scale algal blooms in many areas. Specialized zooplankton filter suspended particles, enhancing transparency. This clarity allows deeper light penetration compared with many freshwater systems, though light still diminishes with depth. Even with exceptional clarity near the surface, most of the lake's volume exists in darkness. Exploration below certain depths relies entirely on artificial illumination. Cameras capture images of sediments, rock formations, and organisms adapted to low-light environments. Lighting choices influence observation results, requiring careful methodological consideration. Chemical composition varies subtly across regions. Trace minerals, dissolved gases and organic compounds reflect tributary inputs, hydrothermal vent contributions and biological activity. Mapping these variations across such a vast volume remains an ongoing scientific effort. Hydrothermal vents contribute mineral-rich water to specific deep areas. Although not as extreme as oceanic vents, they still influence local chemistry. Studying these contributions helps researchers understand geochemical cycling within the lake. Water density differences, influenced by temperature and mineral content, create stratification layers. These layers affect how nutrients and oxygen move vertically. Seasonal changes can alter stratification strength, influencing biological productivity patterns. The enormous water reserve also shapes local climate. Large bodies of water, moderate temperature fluctuations in surrounding regions. Baikal's presence influences humidity, wind patterns, and seasonal temperature extremes in adjacent Siberian areas. Understanding these microclimatic effects requires atmospheric as well as hydrological study. Ice formation each winter covers much of the lake's surface. Ice thickness can exceed a metre in some areas. Beneath that ice lies the full depth of water, insulated from direct atmospheric interaction. Studying winter conditions often involves drilling through ice to access underlying water layers. Ice transparency sometimes allows light penetration, supporting under-ice biological activity. However, snow cover on ice reduces light transmission significantly. Researchers measure under-ice productivity to understand seasonal ecological cycles. From a global perspective, Baikal's freshwater reserve holds strategic importance. Discussions about freshwater scarcity increasingly reference large, stable reservoirs. While no serious proposals exist to transport Baikal water internationally on a large scale, the theoretical value of such a reserve enters policy conversations occasionally. Conservation therefore extends beyond regional ecological concerns. Protecting water quality in Baikal has implications for global freshwater security narratives. International scientific collaborations reflect this broader interest. Technological exploration of such a vast volume requires balancing coverage with detail. Remote sensing satellites provide surface data, temperature patterns, ice cover extent, turbidity indicators. In situ instruments provide depth-resolved measurements. Combining these datasets produces more comprehensive understanding. Autonomous underwater vehicles help survey deep regions. Their endurance, however, remains limited by battery capacity and communication constraints. Long-duration missions require careful energy management and retrieval planning. Water sampling at extreme depths involves specialized equipment. Sampling bottles must withstand pressure without contamination. Retrieval procedures must maintain sample integrity for chemical analysis. Each step adds logistical complexity. Biological sampling across depth gradients reveals surprising diversity. Some species inhabit narrow depth ranges defined by temperature, pressure, and nutrient availability. Cataloguing these organisms contributes to broader understanding of freshwater biodiversity. Genetic sequencing techniques have expanded knowledge of microbial diversity in Baikal. Environmental DNA sampling allows detection of organisms without direct capture. These methods reduce ecological disturbance while increasing detection sensitivity. Despite technological progress, fully characterizing the entire water column across such a massive basin remains an ongoing challenge. Data gaps persist in remote areas, particularly during harsh winter conditions when access becomes limited. Long-term monitoring programs attempt to fill these gaps gradually. Fixed observation stations collect continuous data. Periodic research cruises supplement these records. International data sharing agreements improve analytical capacity. Public interest in Baikal often centers on visible features: clear water, dramatic ice formations, unique wildlife. The invisible volume beneath those features receives less attention. Yet it defines the lake's global significance. Understanding that invisible mass of water changes how one perceives the lake, it stops being simply scenic and becomes structurally important to Earth's freshwater balance. That perspective encourages careful stewardship and sustained scientific attention. Human activity around the lake interacts with this vast water body in subtle ways. Agricultural runoff, industrial discharge, and urban wastewater all carry potential impacts. Monitoring programs track nutrient and contaminant levels to detect trends early. Climate change introduces additional variables. Changes in precipitation patterns influence tributary flow. Temperature shifts affect ice duration and surface stratification. Long-term datasets help identify emerging patterns. Water level regulation through downstream hydroelectric infrastructure requires careful coordination to avoid ecological disruption. Maintaining stable lake levels protects shoreline habitats and local communities. Each of these factors illustrates that exploring Baikal's water volume involves far more than measuring depth once and moving on. It requires continuous observation of physical, chemical, and biological processes interacting across an enormous freshwater system. And as that understanding builds, attention naturally shifts toward what lives within this immense volume, because a reservoir of that size, isolated for millions of years, has given rise to ecosystems that challenge familiar expectations about freshwater biodiversity. When you stand on the shore of Lake Baikal and look out across its surface, what you see is calm water stretching toward a distant horizon. Wind may ripple it, sunlight may reflect sharply off it, ice may seal it over in winter. But what remains hidden beneath that surface is not a simple continuation of what you expect from a typical lake. It is an entire biological system that developed in isolation for millions of years, shaped by cold, pressure, darkness, and geological instability. More than half of the species living in Lake Baikal are endemic. That means they exist nowhere else on Earth. This alone sets the lake apart from most freshwater systems. Endemism at that scale does not happen quickly. It requires time, stability, and environmental uniqueness. Baikal has had all three. One of the most well-known inhabitants is the Baikal seal, or nerpa. It is the only exclusively freshwater seal species in the world. How a seal came to inhabit an inland lake, thousands of kilometers from the nearest ocean, remains a topic of research and debate. The most widely supported theory suggests that ancestors of the nerpa migrated from the Arctic Ocean through river systems during ancient glacial periods. Over time, as ice retreated and routes closed, the population became isolated within the lake. Isolation is a powerful evolutionary force. Once cut off from marine relatives, the Baikal seal adapted to freshwater conditions. Its diet shifted to local fish species. Its physiology adjusted to the lake's temperature and salinity profile. Today, the nerpa is fully integrated into Baikal's ecosystem, an apex predator within this enclosed freshwater world. Fish diversity in the lake is equally distinctive. The omul, a salmonid species endemic to Baikal, has long supported local fisheries. It occupies a central place in regional culture and economy. Monitoring its population requires careful management because overfishing, climate variability, and ecological shifts can influence stock levels. Then there are the golem yankas, translucent fish that lack swim bladders and give birth to live young rather than laying eggs. They inhabit deeper waters and represent one of Baikal's most unusual evolutionary adaptations. Their bodies are composed largely of oil, which helps regulate buoyancy in the cold, high-pressure environment of the lake's depths. Crustaceans dominate much of Baikal's invertebrate life. Amphipods, small shrimp-like creatures, exist in hundreds of species forms. Some are transparent, some are armoured. Others exhibit specialised appendages adapted to specific ecological niches. They serve as both scavengers and prey, forming crucial links in the food web. Sponges in Baikal grow to remarkable sizes compared to their relatives in other freshwater systems. These green sponges, often attached to rocky substrates, harbour symbiotic algae that give them their coloration. The clarity of Baikal's water allows enough light penetration in shallower regions to support this relationship. However, sponge health has fluctuated in recent years, drawing scientific attention to potential environmental stresses. Microbial life constitutes an even more complex and less visible layer of the ecosystem. Bacteria and archaea populate sediments, water columns, and hydrothermal vent zones. Some metabolize chemical compounds released from geological activity. Others participate in nutrient cycling processes that influence overall lake productivity. Environmental DNA studies have revealed microbial diversity far beyond what traditional sampling methods detected. Each new sequencing effort uncovers previously unknown genetic signatures. These findings expand understanding of how life adapts to extreme cold and nutrient-limited conditions. Exploring this biological world requires tailored methodologies. Shallow water surveys involve divers, underwater cameras, and direct sampling. Deeper investigations rely on remotely operated vehicles equipped with manipulator arms, suction samplers, and high-resolution imaging systems. Visibility varies with depth and season. In the clearest conditions near the surface, divers can observe complex sponge communities and fish schools directly. In deeper zones, artificial lighting reveals sediment plains dotted with amphipods, and occasional larger organisms adapted to low light. Pressure at depth shapes morphology. Some organisms exhibit soft gelatinous bodies that withstand compression. Others have reduced skeletal structures. Evolution under constant cold also influences metabolic rates, often resulting in slower growth and longer lifespans compared to similar species in warmer environments. Reproductive strategies differ as well. In a lake where seasonal cycles include extended ice cover and low temperatures, timing reproduction to optimize survival becomes critical. Some species spawn under ice. Others release larvae during specific temperature windows in spring. Food webs in Baikal rely heavily on planktonic productivity. Phytoplankton capture sunlight in upper layers, forming the base of the system. Zooplankton graze on phytoplankton, and larger organisms feed upward through successive trophic levels. Monitoring plankton dynamics helps scientists understand shifts in overall ecosystem health. Climate variability influences plankton blooms. Warmer surface temperatures can alter bloom timing and intensity. Even slight changes in stratification patterns may cascade through the food web. Long-term datasets are essential for identifying such trends. Invasive species pose another concern. Although Baikal has remained relatively insulated due to its remote location and strict environmental regulations, global trade and tourism always carry some risk. Maintaining endemic biodiversity requires vigilance against non-native introductions. Parasites and disease dynamics within the lake also warrant attention. The Baikal seal population experienced a significant die-off event in the late 20th century, likely linked to viral infection. Monitoring wildlife health now forms part of ongoing conservation efforts. Hydrothermal vent zones support specialized microbial communities distinct from surrounding waters. Sampling these communities requires precision to avoid contamination. Understanding their metabolic pathways provides insight into life in chemically unique environments. Some researchers compare Baikal's deep ecosystems to those found in certain oceanic environments, despite differences in salinity. The combination of cold, pressure, and limited light creates parallel challenges for organisms. Studying these parallels helps broaden knowledge of evolutionary adaptation. Acoustic monitoring occasionally detects biological sounds within the water column. Fish movements, seal vocalizations, and ice cracking produce a dynamic soundscape. Analyzing acoustic patterns assists in tracking species presence and behavior. Winter conditions reshape biological activity. Ice cover reduces light penetration but stabilizes surface conditions. Some organisms enter slower metabolic states. Others remain active, taking advantage of reduced predation or altered nutrient distribution. Spring melt triggers renewed productivity. As ice retreats, increased light stimulates phytoplankton growth. Zooplankton populations respond accordingly. Monitoring these seasonal pulses reveals how tightly biological cycles align with physical processes. Research into Baikal's biodiversity often intersects with broader evolutionary questions. How do isolated systems generate such high endemism? What genetic mechanisms support adaptation to extreme cold? How resilient are these specialized species to environmental change? Conservation programs incorporate community engagement. Local fishers participate in monitoring efforts. Educational initiatives raise awareness about protecting endemic species. Balancing economic activity with ecological preservation remains an ongoing challenge. Scientific publications about Baikal's biology continue expanding. Yet even with decades of study, new species descriptions appear regularly. Each discovery underscores how much remains undocumented beneath the surface. Technological improvements enhance exploration capacity. High-definition imaging reveals fine morphological details. Autonomous sampling platforms extend survey reach. Yet complete coverage of such a vast and deep ecosystem remains impractical within short timeframes. Understanding predator-prey relationships requires sustained observation. Tagging programs track seal movements. Fish population studies monitor migration patterns within the lake's length. Data integration across species builds a more coherent ecological picture. Some deep zones remain sparsely studied due to access difficulty. Steep underwater slopes, sediment instability, and limited dive duration constrain exploration. These constraints contribute to the sense that portions of Baikal's biological world remain partially unseen. Even well-studied species sometimes reveal unexpected traits under closer examination. Genetic studies may uncover hidden diversity within what was once considered a single species. Behavioral observations may challenge earlier assumptions about feeding or reproduction. The interplay between geology and biology becomes especially clear near tectonic features. Fault lines influence sediment deposition, which in turn shapes habitat structure. Organisms adapt to these microenvironments, adding further complexity to the system. As climate patterns evolve, scientists watch closely for shifts in species distribution. Temperature-sensitive organisms may adjust depth ranges. Plankton communities may reorganize. Long-term ecological research sites provide valuable reference points for detecting change. Public fascination often focuses on charismatic species like the Nerpa. However, the lake's stability depends equally on less visible organisms performing essential ecological functions. Microbes cycling nutrients and amphipods recycling organic matter play roles just as critical as larger predators. Each layer of life beneath Baikal's surface interconnects with physical processes above and below. Water chemistry, temperature gradients, geological activity, and seasonal cycles all feed into biological outcomes. Exploration therefore becomes an exercise in interdisciplinary collaboration. Biologists depend on geologists for basin mapping. Chemists provide nutrient analyses. Climate scientists contribute predictive modelling. Engineers maintain equipment capable of operating in extreme conditions. And as this integrated understanding grows, attention naturally turns toward the specific environmental pressures that define life at depth. Because descending further into Baikal means confronting conditions of darkness, pressure, and cold that shape not only organisms, but also the limits of human technology attempting to observe them. If you move gradually from Lake Baikal's shoreline into deeper water, the first changes feel familiar. Light dims slightly, temperature drops a little. Fish species shift as depth increases. Nothing too unexpected at first, but continue descending, and eventually you reach a point where ordinary assumptions about freshwater life start to break down. Sunlight fades almost completely. Water temperature stabilizes just above freezing. Pressure increases steadily, and yet life continues there in forms specifically adapted to these conditions. Cold dominates the Baikal environment from top to bottom, but especially at depth. Surface waters may warm modestly during summer months, though rarely to levels considered warm by global standards. Beneath those upper layers, however, temperatures remain consistently low year-round, often hovering close to freezing. For organisms living there, metabolic processes slow accordingly. Growth rates decrease, lifespans often extend. Reproductive cycles adapt to long intervals rather than rapid turnover. Fish species inhabiting deeper zones illustrate these adaptations clearly. The golomyanka, already mentioned earlier, serves as a particularly striking example. Its semi-transparent body reflects an environment where camouflage relies less on coloration and more on minimizing visual profile altogether. Without a swim bladder, it maintains buoyancy through high lipid content, an adaptation well suited to cold, high-pressure freshwater conditions. Golomyankas exhibit behaviours uncommon among freshwater fish. Instead of laying eggs externally, females give birth to live young. This reproductive strategy may improve offspring survival in cold environments, where egg development would otherwise take extended periods and face greater predation risk. Such adaptations highlight how isolation and environmental pressure shape evolutionary outcomes over millions of years. Amphipods represent another major group thriving in Baikal's cold depths. Hundreds of species exist, occupying various ecological niches. Some specialize as scavengers, breaking down organic material settling from upper layers. Others function as predators or grazers. Their morphological diversity reflects long evolutionary experimentation within a stable yet demanding environment. Many amphipods display reduced pigmentation. In darkness, bright coloration provides little advantage. Energy conservation becomes more important than visual signaling. Some species also exhibit enlarged sensory appendages, helping detect chemical cues or subtle water movements in low visibility conditions. Sponges inhabiting deeper rocky substrates provide habitat complexity. Their porous structures shelter smaller organisms. Symbiotic relationships with microorganisms influence nutrient cycling. While shallow water sponges benefit from some light penetration supporting algal symbionts, deeper forms rely entirely on filter feeding. Microbial communities dominate the deepest ecological layers. Bacteria and archaea metabolize organic matter descending from above, or chemicals emerging from geological sources. These microorganisms form the base of deep-water food webs independent of direct sunlight. Hydrothermal vent zones introduce additional biological specialization. Though less extreme than oceanic vents, they still alter local temperature and chemical composition. Microbial mats near these vents demonstrate metabolic pathways capable of utilizing chemical energy rather than photosynthesis. Studying such communities informs broader questions about life in extreme environments beyond Earth. Cold water increases oxygen solubility, and Baikal's depths remain oxygenated compared with many deep lakes. This oxygen availability supports more complex life than would otherwise be possible. Yet maintaining oxygen distribution across such depth requires physical mixing processes influenced by basin shape, seasonal winds and temperature gradients. Pressure at depth also shapes biological form. Flexible tissues often replace rigid skeletal structures. Some organisms exhibit gelatinous consistency, allowing them to withstand compression without structural damage. Studying these adaptations provides insight into how life copes with hydrostatic pressure in freshwater contexts. Darkness presents another constant challenge. Without light, visual hunting strategies lose effectiveness. Sensory systems relying on vibration detection, chemical cues, or electroreception become more important. Fish species may develop enlarged lateral line systems to detect minute water movements. Bioluminescence, common in ocean depths, appears less prevalent in Baikal, though research continues. Freshwater chemistry and evolutionary history influence whether light-producing mechanisms develop. Absence of bioluminescence does not imply absence of complex communication systems. Chemical signaling may fulfill similar roles. exploration of these environments requires specialized technology. Remotely operated vehicles equipped with pressure-resistant housings descend slowly to avoid disturbing sediments. Cameras utilize lighting calibrated to minimize behavioral disruption. Sampling arms collect specimens cautiously to preserve fragile structures. Even with careful methodology, observation influences environment. Artificial light may attract or repel organisms. Vehicle noise generates vibrations. Researchers account for these effects when interpreting data, yet complete neutrality remains impossible. Long-term monitoring instruments placed on the lake floor record temperature, pressure, oxygen levels, and occasionally acoustic signals. These datasets help identify seasonal patterns and rare events, such as underwater landslides or unusual biological activity. Cold conditions affect research equipment as much as organisms. Batteries lose efficiency. Lubricants thicken. Electronics require insulation. Designing instruments capable of operating reliably for months or years in near-freezing fresh water remains an engineering challenge. Biological sampling campaigns often reveal new species even in well-studied regions. Advances in genetic sequencing accelerate identification of microorganisms previously undetectable. Each discovery adds complexity to ecological models. Food availability in deep Baikal waters depends partly on organic matter descending from surface productivity. This marine snow equivalent in fresh water consists of plankton remains, fecal pellets, and detritus. Scavengers and microbes recycle these materials, sustaining deeper ecosystems. Seasonal productivity pulses influence how much organic material reaches depth. Spring phytoplankton blooms increase particulate descent. Winter conditions reduce input. Organisms adapt feeding strategies accordingly, sometimes storing energy reserves during productive periods. Predator-prey relationships adjust to low-light environments. Ambush strategies relying on vibration detection replace visually guided pursuit. Some amphipods exhibit opportunistic feeding behaviors, consuming whatever organic matter becomes available. Parasite-host interactions occur even at depth. Studying these relationships contributes to understanding ecosystem health. Changes in parasite prevalence sometimes signal broader environmental shifts. Climate change research increasingly examines deep water responses. Surface warming might alter stratification strength, affecting oxygen transport downward. Even subtle shifts could influence species adapted to stable cold conditions. Conservation discussions extend to deep water habitats, while human activity impacts surface zones more directly. Pollution eventually disperses throughout the water column. Monitoring contaminant levels at depth helps assess long-term ecosystem resilience. Educational outreach about Baikal often focuses on visible wildlife, yet explaining deep water ecosystems enhances appreciation for the lake's complexity. Public understanding supports conservation policy and research funding. International collaborations bring diverse expertise to Baikal studies. Polar researchers contribute cold environment experience. Marine biologists offer deep water methodological insights. Limnologists provide freshwater system knowledge. Interdisciplinary cooperation proves essential. Local communities also hold observational knowledge accumulated over generations. Seasonal patterns, unusual wildlife sightings, and environmental changes reported by residents complement formal scientific data. As exploration technology improves, deeper zones become more accessible. Yet accessibility does not equal complete understanding. Each new observation often raises additional questions about ecological interactions and evolutionary history. Understanding creatures of the cold and dark requires patience. Biological processes operate slowly. Long-term datasets reveal trends invisible in short studies. Consistency in methodology ensures comparability across decades. Research funding cycles sometimes struggle to align with such long temporal scales. Sustained investment remains necessary to capture gradual ecological changes. Baikal's isolation has preserved unique biodiversity, but isolation also increases vulnerability. Species with narrow environmental tolerances may respond strongly to even minor disturbances. Monitoring helps identify early warning signs. The lake's biological richness contributes to its global scientific importance. Studying endemic species informs evolutionary biology, climate science, and conservation strategy development. And once attention settles on how life persists under such cold, dark, high-pressure conditions, the next question naturally emerges about the physical environment itself, because descending further into Baikal means confronting not just biological adaptation, but the fundamental challenges of pressure, darkness, and silence that shape both ecosystems and human attempts to explore them. If you were to lower a camera slowly into Lake Baikal and watch the live feed from the surface, the first part of the descent would look familiar. Rippling light patterns dance across suspended particles. Fish move through the upper layers. Colours remain recognisable. But as the camera continues downward, light weakens. Blue fades into grey. Then grey dissolves into near black. Eventually, the only illumination comes from the equipment itself. Depth in Baikal is not just a number on a sonar display. It is a physical transformation of environment. At around 200 meters, sunlight penetration becomes extremely limited. By the time you approach 1,000 meters, natural light is effectively absent. The lake's deepest zones exist in permanent darkness, unaffected by sunrise or sunset. Darkness alone changes the rules of exploration. Human vision depends on light. Cameras require it. Artificial lighting becomes essential below certain depths, yet introducing light into a dark adapted environment can influence behaviour. Organisms may retreat, freeze, or react unpredictably. Observations must account for these responses. Pressure increases steadily with depth. For every 10 metres of descent, pressure rises by roughly 1 additional atmosphere. At Baikal's maximum depth, pressure exceeds 160 atmospheres. That force acts on every surface. Equipment housings, sensor casings, submersible walls, and the bodies of organisms adapted to endure it. Engineering for such pressure in fresh water involves subtle differences compared to marine environments. Saltwater has higher density, affecting buoyancy calculations. Freshwater pressure exerts force differently in terms of corrosion and material interaction. Designers must account for these distinctions when building instruments for Baikal's depths. Seals and housing materials must resist compression without deformation. Even minor structural weaknesses can compromise equipment integrity. Long-term deployments require materials that maintain resilience under constant high-pressure exposure. Temperature compounds the challenge. Deep Baikal water remains just above freezing year-round. Cold increases material brittleness. Lubricants thicken, battery efficiency decreases, electronic components require insulation and energy management systems capable of functioning reliably in near-freezing conditions for extended periods. Silence defines much of the deep environment. Unlike shallow waters where wave action and surface wind create constant background noise, deeper zones experience minimal mechanical disturbance. Sound travels efficiently through water, yet the absence of surface-generated noise creates an environment where subtle vibrations become significant. Researchers studying acoustic properties of Baikal have noted how ice cover in winter further alters sound transmission. Ice acts as a reflective boundary, trapping certain frequencies within the water column. This phenomenon influences how sound propagates and how biological and geological events are detected. Seismic activity beneath the lake produces low-frequency vibrations. Acoustic sensors placed on the lake floor capture tremors too small to be felt at the surface. These recordings help map tectonic activity within the rift basin. Biological sounds contribute to the underwater soundscape as well. Fish movement generates subtle disturbances. Amphipods interacting with sediment produce faint vibrations. Seal vocalizations, when present, travel considerable distances through cold water. Operating remotely operated vehicles in such quiet conditions requires careful propulsion control. Thruster noise can dominate the sound environment. Minimizing mechanical disturbance improves observational quality and reduces impact on wildlife. Darkness presents navigational difficulties. Without visual reference points, ROV operators rely on sonar and inertial navigation systems. Steep underwater slopes and sediment plumes can obscure sonar readings, requiring cautious maneuvering. Sediment composition affects exploration as well. Fine particles disturbed by vehicle movement can create turbidity clouds, reducing visibility even under artificial lighting. Operators must maintain distance from the lake floor to avoid unnecessary disturbance. Pressure differentials also influence sampling techniques. Collecting water samples at depth requires bottles that seal automatically to prevent pressure-induced contamination. Upon retrieval, decompression may alter dissolved gas content, requiring careful handling and analysis protocols. Biological specimens brought to the surface sometimes exhibit stress responses due to pressure change. Certain deep adapted organisms cannot survive rapid decompression. Scientists therefore employ pressure-retaining containers when studying delicate species. Human divers cannot reach Baikal's deepest zones. Even advanced technical diving remains limited to much shallower depths. Exploration below those limits depends entirely on mechanical systems and remote operation. The psychological aspect of deep exploration should not be overlooked. Watching live video from a submersible descending into complete darkness creates a distinct awareness of isolation. The distance between surface and vehicle becomes tangible. Communication delays, though minimal in tethered systems, remind operators of separation. Data transmission from deep deployments sometimes relies on tether cables. These cables limit operational radius and risk entanglement. Autonomous vehicles expand range but sacrifice real-time control and require precise programming. In winter, deploying deep instruments through ice involves drilling access holes large enough for equipment passage. Ice thickness must be measured carefully. Weather conditions determine safe working windows. Beneath the ice, darkness is nearly complete even at moderate depths. Silence under ice often feels amplified. Without surface wave noise, acoustic clarity improves. This clarity benefits seismic and biological monitoring, but also emphasizes mechanical sounds generated by equipment. Studying pressure effects on organisms reveals biochemical adaptations. Cell membranes in deep-water species maintain fluidity at low temperatures and high pressure through specialized lipid compositions. Enzymes function efficiently despite environmental constraints. Comparisons between Baikal deep-water organisms and marine deep-sea species highlight convergent evolution. Despite freshwater chemistry differences, similar environmental pressures produce analogous adaptations. Exploration technology borrowed from oceanographic research adapts to Baikal with modifications. Pressure ratings may be sufficient, but freshwater corrosion patterns differ. Testing under controlled conditions precedes field deployment. Even with robust equipment, maintenance cycles are frequent. Cold water intrusion into connectors can cause failures. Pressure seals require inspection. Spare parts logistics in remote Siberia add complexity. Environmental monitoring arrays often include multiple sensors spaced across depth gradients. Data retrieval schedules align with seasonal access windows. Long winters delay certain maintenance operations. Silence in the deep also affects predator-prey dynamics. Acoustic cues become more prominent when visual information disappears. Some species may rely heavily on vibration detection to locate food or avoid threats. Researchers sometimes deploy baited camera systems to attract organisms into view. Observing feeding behavior under artificial lighting offers insight into trophic relationships. However, bait introduces temporary ecological disturbance and must be used judiciously. Hydrostatic pressure also influences chemical reactions. Dissolved gas solubility varies with depth. Understanding these gradients informs models of oxygen distribution and nutrient cycling. Instruments measuring dissolved gases require calibration across pressure ranges. Pressure effects on sensor membranes must be accounted for to avoid systematic errors. Exploration under such conditions demands patience. Descent to maximum depth can take hours. Careful navigation across the lake floor proceeds slowly to prevent sediment disruption. Retrieval requires equal caution. Each deep mission generates vast data volumes, video footage, chemical readings, acoustic recordings, temperature logs. Analysing this information extends long beyond the field season. Funding constraints sometimes limit mission frequency. Harsh environmental conditions shorten operational windows. Coordinating multidisciplinary teams within these constraints challenges research planning. Despite these difficulties, each descent contributes incremental knowledge. Observing previously unseen zones expands ecological maps. Recording seismic tremors refines geological models. Measuring oxygen levels across depth informs climate impact assessments. The combination of pressure, darkness and silence defines Baikal's deepest character. It shapes not only the organisms living there, but also the strategies humans use to study it. And as those strategies evolve, attention inevitably turns toward another limiting factor in exploration, because even when pressure-resistant equipment and artificial lighting allow descent into darkness, the simple physics of light absorption in water ensures that visibility remains fundamentally restricted in ways that continue to constrain what can truly be seen. If you have ever leaned over the edge of a clear lake on a sunny day, you may have noticed how quickly water begins to obscure what lies below. Even when the surface looks perfectly transparent, details fade after a short distance. Colours dull first, then shapes soften, and eventually everything dissolves into a uniform shade. That familiar experience becomes far more pronounced in Lake Baikal, not because the water is murky, but because physics itself limits how far light can travel through water, no matter how clear it appears. Water absorbs light steadily as depth increases. Different wavelengths disappear at different rates. Reds vanish first, then oranges, then yellows. Blues and greens penetrate farther, which is why deep water often appears blue from above. But even those wavelengths eventually fade. At several hundred meters in Baikal, natural light becomes so weak that visual observation without artificial illumination is effectively impossible. Clarity alone does not change this fundamental rule. Baikal is famous for exceptional transparency near the surface. In some conditions, visibility can exceed 40 meters, sometimes more. That level of clarity results from low nutrient levels, efficient plankton filtration, and relatively limited sediment disturbance in certain areas. Yet even this remarkable transparency cannot overcome the exponential decay of light with depth. This creates an interesting contrast. Near the surface, Baikal may appear almost glass-like. Photographs taken from boats or shore often capture submerged rocks clearly visible through meters of water. Visitors sometimes assume that such clarity extends indefinitely downward. It does not. Beyond a certain depth, the absence of sunlight is absolute. For exploration, this means that visual mapping of deep zones always depends on artificial lighting. Remotely operated vehicles carry high-intensity lamps designed to illuminate surrounding terrain. Cameras capture images within that limited cone of light. Everything beyond it remains unseen. Artificial lighting introduces practical complications. Strong lights consume power quickly. Battery capacity limits mission duration, particularly for autonomous vehicles. Tethered systems can supply external power, but tethers restrict mobility and risk entanglement along steep underwater slopes. Light scattering further complicates observation. Even in very clear water, microscopic particles scatter artificial light. This backscatter effect can reduce image contrast and obscure fine details. Engineers design lighting angles carefully to minimize this phenomenon, yet it cannot be eliminated entirely. Color distortion also affects interpretation. Artificial lights attempt to restore full spectrum illumination, but camera sensors and water absorption still alter color perception. Biological specimens photographed at depth may appear different once brought to the surface under natural light. For biological studies, light intrusion can influence behaviour. Organisms adapted to darkness may retreat when illuminated. Some freeze motionless, others move unpredictably. Researchers consider these responses when analysing video footage, recognising that what they observe may reflect reaction rather than normal activity. Acoustic imaging offers an alternative to visual observation. Sonar systems emit sound waves and interpret returning echoes to create topographic maps. Because sound travels efficiently through water, sonar can survey areas far beyond the reach of light. However, sonar provides structural information rather than detailed visual imagery. Combining sonar mapping with targeted visual inspections helps build comprehensive understanding. Sonar identifies features such as ridges, slopes, or sediment plains. Remotely operated vehicles then investigate specific sites with cameras and sampling tools. Sediment composition influences light penetration locally. Areas near river inflows may contain higher suspended particle concentrations, reducing clarity even in shallower zones. Seasonal storms or underwater landslides can temporarily increase turbidity. Winter conditions add another dimension. Ice cover reduces surface light transmission. Snow accumulation on ice further limits penetration. Under ice exploration often occurs in near total darkness, even at modest depths, requiring artificial lighting almost immediately after descent. Surface weather conditions affect light entry as well. Cloud cover, wave action, and sun angle all influence how much light reaches the water column. Long Siberian winters produce extended periods of low solar elevation, reducing overall light input. Photosynthetic organisms cluster within upper layers where light remains sufficient. This photic zone supports phytoplankton growth, forming the base of the food web. Below that zone, ecosystems rely increasingly on organic matter descending from above or on chemical energy sources. Understanding the depth of the photic zone helps model biological productivity. Researchers measure light intensity at various depths using radiometers. These measurements inform ecological models predicting plankton growth patterns and seasonal cycles. Hydrothermal vent zones provide localized exceptions to the sunlight-driven ecosystem model. There, chemical energy supports microbial communities independent of photosynthesis. Such systems remain relatively rare in freshwater, but illustrate alternative energy pathways. Technological advances attempt to extend visual reach. Improved camera sensitivity allows imaging under lower light levels. Enhanced noise reduction algorithms clarify images captured with minimal illumination. Yet fundamental absorption limits remain unchanged. Laser scanning systems sometimes supplement imaging. Narrow beams penetrate slightly farther than broad-spectrum light, enabling precise distance measurements. However, lasers still experience attenuation with depth and suspended particles. Human divers exploring shallow Baikal waters notice colour loss directly. Red equipment appears grey at depth. Skin tones shift. Natural coloration fades. These observations mirror what cameras record deeper down. The absence of light shapes evolutionary pathways. Organisms adapt by enhancing non-visual sensory systems. Chemical detection, vibration sensitivity, and tactile perception become more important than eyesight. Some deepwater fish exhibit reduced eye size. Maintaining complex visual organs consumes energy. In darkness, that investment offers limited return. Evolution therefore reallocates resources toward other sensory adaptations. Artificial illumination occasionally reveals unexpected biological behaviour. Certain amphipods gather around light sources, possibly interpreting them as cues for organic matter presence. Such interactions require careful interpretation. Long-term camera stations placed at depth operate intermittently to conserve power. Time-lapse imaging captures slow environmental changes. These datasets reveal sediment movement patterns and occasional biological activity. Light limitation also affects human perception of completeness. exploration often relies on seeing. When large areas remain visually inaccessible, a psychological sense of partial knowledge persists even when acoustic or chemical data exist. Researchers therefore integrate multiple data types. Visual imagery provides context. Sonar supplies structural mapping. Chemical analyses reveal water composition. Biological sampling identifies species presence. Together they approximate comprehensive understanding. Satellite remote sensing contributes surface information only. Ice cover extent, surface temperature and turbidity patterns can be observed from orbit. Depth processes remain invisible from space, reinforcing reliance on in situ instrumentation. Educational outreach sometimes emphasizes Baikal's clarity without explaining depth-related darkness. Clarifying this distinction helps public understanding of exploration challenges. Photography enthusiasts visiting the lake often capture striking surface images. Underwater photographers working at shallow depths document sponge communities and fish species vividly. Deeper photographic work requires specialized submersibles beyond recreational capability. Engineering considerations for lighting systems include heat dissipation. High-intensity lamps generate heat even in cold water. Thermal management prevents equipment damage while maintaining efficient illumination. Battery chemistry research continues seeking solutions for cold environment energy storage. Improved energy density and cold temperature performance would extend mission durations for deep exploration. Despite technological progress, the fundamental fact remains: light attenuates exponentially in water. No level of clarity eliminates that reality. At Baikal's deepest points, darkness is permanent, and recognizing that permanent darkness naturally leads to considering another environmental constraint, because even if visibility could somehow be extended indefinitely, the extreme cold permeating Baikal's depths imposes additional limits on both biological systems and the machines humans send downward to study them. If you were to lower a thermometer into Lake Baikal and watch the reading change as it descended, you would notice something that at first feels counterintuitive. Instead of fluctuating dramatically, the temperature stabilizes. Below the upper seasonal layers, the water remains consistently cold, usually just above freezing. That stability may sound comforting, but in practice it creates one of the most persistent constraints on exploration and on the living systems that exist there. Cold water behaves differently from warm water in almost every physical, chemical and biological sense. Molecular motion slows. Chemical reactions proceed more gradually. Mechanical systems require more energy to function efficiently. Biological metabolism adjusts to reduce thermal energy. Everything continues but at a different pace. For living organisms in Baikal, cold is not a seasonal inconvenience. It is the default condition. Evolution has shaped species that operate reliably near freezing temperatures. Enzymes within their cells function optimally in cold environments. Membrane structures remain flexible despite reduced molecular motion. Energy budgets emphasize efficiency rather than speed. Fish species inhabiting deeper zones illustrate this clearly. Growth rates tend to be slower than in warmer freshwater systems. Lifespans often extend accordingly. Reproductive cycles may occur less frequently. These patterns reflect the trade-off between metabolic demand and environmental energy availability. The Baikal seal offers another example. Maintaining body temperature in cold water requires substantial energy expenditure. Thick blubber layers provide insulation. Behavioral adaptations, such as hauling out on ice or sheltered shorelines, help conserve heat. Understanding these adaptations contributes to broader knowledge of thermoregulation in cold aquatic mammals. Microbial communities also adjust metabolic pathways. Certain bacteria possess enzymes specifically adapted to cold environments, often called psychrophilic enzymes. These enzymes maintain catalytic activity at low temperatures, where typical enzymes would function poorly. Studying them has applications in biotechnology, including cold temperature industrial processes. Cold influences oxygen dynamics as well. Oxygen dissolves more readily in cold water than in warm water. This characteristic contributes to Baikal's unusual ability to maintain oxygenated deep layers. However, oxygen distribution still depends on mixing processes and biological consumption rates. For exploration technology, cold presents persistent engineering challenges. Batteries lose efficiency at low temperatures. Chemical reactions within battery cells slow, reducing available power. Researchers often insulate battery compartments or incorporate heating elements, though heating consumes energy and shortens operational duration. Lubricants used in mechanical components behave differently in cold water. Viscosity increases, potentially hindering moving parts. Specialized lubricants designed for low-temperature performance become necessary. Even then, maintenance cycles must account for gradual degradation. Electronic components face condensation risks when equipment transitions between temperature zones. Moisture accumulation inside housings can cause short circuits or sensor malfunctions. Engineers design sealing systems and thermal buffers to mitigate these risks. Cold also affects acoustic properties. Sound travels slightly differently in cold water, influencing sonar calibration. Accurate mapping requires adjusting for temperature-dependent sound speed variations. These adjustments become especially important in deep water surveys. Human operations around the lake must adapt as well. Fieldwork during winter involves extreme air temperatures far below freezing. Equipment transported from warm indoor environments to outdoor conditions requires acclimatization to prevent material stress or failure. Ice cover introduces additional thermal considerations. Beneath ice, water temperature stabilizes further. Surface mixing reduces, affecting oxygen transport and nutrient distribution. Monitoring under ice conditions requires drilling access holes and maintaining equipment in freezing air while it operates in near-freezing water. Cold slows corrosion processes in some contexts, but accelerates others depending on material composition and water chemistry. Understanding these interactions informs equipment material selection and maintenance planning. Biological observation in cold environments requires patience. Organisms move more slowly. Behavioral events occur over longer timescales. Time-lapse imaging often captures ecological processes more effectively than continuous high-speed recording. Sediment decomposition proceeds gradually in cold water. Organic material descending from upper layers breaks down slowly, influencing nutrient recycling rates. This slow decomposition contributes to Baikal's water clarity and ecological stability. Seasonal warming near the surface creates stratification layers. These layers influence mixing patterns, nutrient transport, and biological productivity. Modelling stratification requires accurate temperature profiles across depth gradients. Climate change research focuses partly on temperature trends. Even slight warming can alter stratification strength and duration. Monitoring long-term temperature records helps identify subtle shifts that might influence ecosystem stability. Cold also shapes reproductive timing. Some fish species spawn during specific temperature windows. Amphipod life cycles align with seasonal productivity pulses influenced by thermal conditions. Understanding these cycles aids conservation planning. Hydrothermal vent zones present localized temperature anomalies. Although still relatively cold compared with oceanic vents, these areas offer slightly warmer microhabitats. Microbial communities adapt to these gradients, adding diversity to deep-water ecosystems. Laboratory studies of Baikal organisms often replicate cold conditions to maintain physiological integrity. Transporting specimens to warmer facilities without temperature control risks altering biological characteristics before analysis. Cold water diving, even at shallow depths, requires specialized gear. Thermal protection becomes critical. Extended exposure without proper insulation can impair diver performance and safety. Deeper exploration relies entirely on remotely operated systems due partly to these thermal constraints. Data logging equipment deployed long-term must operate reliably despite cold. Temperature sensors, oxygen probes, and chemical analyzers require calibration stability over months or years. Cold-induced drift must be accounted for during data analysis. Logistical planning for expeditions incorporates thermal considerations. Transporting fuel, food, and equipment in sub-freezing conditions requires insulation strategies. Vehicle maintenance schedules adapt to cold weather wear patterns. Local communities around Baikal have long adapted to these thermal realities. Traditional fishing methods account for ice thickness and seasonal temperature patterns. Indigenous knowledge contributes valuable observational insights complementing scientific measurements. Tourism activities also reflect cold influence. Winter ice roads provide transportation routes across parts of the lake. Ice stability monitoring ensures safety. However, unpredictable temperature fluctuations can alter ice conditions rapidly. Cold water clarity enhances photographic opportunities near the surface, but does not extend indefinitely downward, as discussed earlier. Combining clarity with low temperature creates visually striking yet technically demanding exploration environments. Engineering research continues exploring materials optimized for cold freshwater conditions. Advances in polymer flexibility, battery chemistry, and electronic insulation promise gradual improvements in exploration capability. Despite these advances, cold remains a fundamental environmental constant. It slows biological metabolism, chemical reactions, mechanical operations, and sometimes human decision-making simply by increasing operational complexity. Understanding this pervasive cold helps explain why exploration proceeds methodically rather than rapidly. Each mission requires preparation for conditions that resist haste, and once the influence of temperature becomes clear, attention naturally shifts toward how surface conditions interact with this cold environment. Because during winter, the lake's ice cover introduces another layer of complexity that affects both the ecosystems below and the human efforts to study them. When winter settles over Lake Baikal, the transformation is not subtle. Air temperatures plunge far below freezing. Snow gathers along the shoreline, wind sweeps unhindered across open stretches, and gradually, the vast surface of the lake begins to harden. At first, thin sheets of ice form along protected bays and shallow edges. These sheets thicken steadily as cold persists. Eventually, much of the lake becomes sealed beneath a solid layer that can exceed a meter in thickness. Standing on that frozen surface can feel disorienting. Beneath your boots lies not solid earth, but one of the deepest freshwater bodies on the planet. It is tempting to think of ice as static. Frozen water suggests stillness, permanence, immobility. But Baikal's ice is anything but lifeless. It shifts, expands, contracts, and fractures in response to temperature changes, wind stress, and subtle tectonic movement below. It breathes and cracks, sometimes with sounds that carry across kilometers. The physics behind these movements is straightforward. Water expands when it freezes. As surface layers solidify, pressure builds within the forming ice sheet. When temperatures fluctuate even slightly, expansion and contraction occur. These forces create tension lines that eventually release in long, jagged cracks. Some cracks stretch for kilometers, others form intricate geometric patterns visible from above. On calm days, these fractures may appear as dark lines slicing through otherwise clear ice. At night, or during sudden temperature drops, the release of stress can produce booming sounds that echo across the frozen expanse. For researchers, ice cover changes the entire dynamic of exploration. In summer, boats and research vessels provide access. In winter, mobility depends on snowmobiles, tracked vehicles, or carefully marked ice roads. Before any heavy equipment moves onto the surface, ice thickness must be measured repeatedly. Thickness varies across the lake. Areas near river inflows may freeze differently due to water movement. Regions above hydrothermal vents can remain thinner. Wind patterns influence snow accumulation, which insulates underlying ice and slows further thickening. Safe travel routes require constant reassessment, yet winter also offers unique opportunities. A stable ice platform allows scientists to drill directly down into specific coordinates without the complication of boat drift. Instruments can be lowered vertically with precision. Long-term monitoring devices may be installed through carefully cut holes. Drilling through ice is not trivial. Ice augers or specialized drilling rigs create access holes often just wide enough for equipment passage. Each hole must be marked clearly to prevent accidents. In extreme cold, maintaining open access requires periodic clearing of refreezing water. Once through the ice, the water below remains at near freezing temperature but unfrozen due to pressure and the insulating properties of the ice layer above. Sampling beneath ice reveals ecological processes that continue despite surface stillness. Light penetration under ice depends heavily on snow cover. Clear ice without snow can transmit significant light, allowing under-ice photosynthesis. Thick snow blocks much of that light, reducing biological productivity in upper layers. Researchers measure light intensity under varying ice conditions to model seasonal energy input. The ice itself becomes an object of study. Gas bubbles trapped during freezing create striking patterns. Methane released from sediments sometimes rises and becomes encapsulated within the ice sheet. Studying these trapped gases provides information about underlying biological and geological processes. Ice movement remains one of the most dynamic aspects of winter Baikal. Wind can push large sections of ice against each other, forming pressure ridges. These ridges may rise several meters above the surface, resembling frozen waves frozen mid-motion. Beneath these ridges, blocks of ice overlap and stack, increasing local thickness unpredictably. Navigating around them requires experience and caution. GPS mapping assists, but real-time visual assessment remains essential. Cracks in the ice can open suddenly. Temperature shifts during the day may cause narrow fissures to widen slightly. Overnight cooling may close them partially. These cycles give the impression that the ice is alive, constantly adjusting to stress. Acoustic monitoring under ice reveals how these surface movements translate into underwater sound. Cracking ice produces sharp acoustic signatures detectable at considerable distances. Differentiating between ice sounds and seismic events requires careful analysis. Ice cover also modifies water circulation. Wind-driven surface mixing ceases. Stratification patterns stabilize. Oxygen transport dynamics shift accordingly. Some areas experience reduced mixing, influencing nutrient distribution. For wildlife, ice presents both challenge and opportunity. Baikal seals use ice for resting and breeding. They maintain breathing holes through the ice, ensuring access to air. Monitoring seal populations during winter involves tracking these breathing sites and observing behavior from a distance to minimize disturbance. Fish behavior adjusts under ice as well. Reduced light alters feeding patterns. Some species retreat to deeper zones. Others exploit stable under-ice conditions for spawning or foraging. Researchers working on the ice must account for environmental hazards beyond cracking. Extreme air temperatures can impair equipment performance and human endurance. Wind chill intensifies exposure risk. Safety protocols include redundant communication systems and emergency planning. Logistical coordination becomes complex during winter expeditions. Fuel transport across ice requires weight distribution planning. Vehicle loads must remain within safe limits, determined by measured ice thickness. These calculations change throughout the season. Climate trends influence ice formation timing and duration. Long-term records indicate gradual shifts in freeze-up and break-up dates. Even small changes can affect ecological cycles and research planning windows. As spring approaches, ice begins to weaken. Meltwater pools form on the surface. Cracks widen. Large sections eventually break apart, drifting under wind influence before dissolving entirely. This breakup period introduces additional hazards, limiting safe surface access. From above, satellite imagery captures the dramatic transition from solid white expanse to fragmented flows. Remote sensing helps track ice extent and thickness over time, contributing to climate research datasets. Public fascination with Baikal's winter landscape often centers on its visual beauty. Clear ice revealing trapped bubbles creates striking images. However, Beneath that beauty lies a dynamic physical system constantly adjusting to stress. For exploration, winter is neither simply obstacle nor advantage. It reshapes access methods, alters ecological conditions, and introduces unique data collection opportunities. Researchers plan annual cycles around both open water and ice-covered seasons. Understanding how ice interacts with water below improves modelling of thermal and chemical exchange processes. It also informs predictions about how warming climates may alter Baikal's future behaviour. And once the complexities of ice movement and seasonal transformation are considered, the next factor influencing exploration becomes evident, because even when surface conditions permit access, the lake's weather can shift rapidly, bringing winds and storms that challenge both equipment and human endurance in ways that further complicate sustained research efforts. If you spend enough time around Lake Baikal, one of the first things you learn is that calm conditions rarely guarantee stability for long. The surface can appear almost motionless, reflecting sky and shoreline with unusual clarity, and then within hours the entire character of the lake shifts. Winds rise, waves build quickly, temperatures drop, and visibility changes. For people accustomed to smaller lakes where weather patterns often feel predictable, Baikal introduces a different scale of atmospheric behaviour. Part of this unpredictability comes from geography. The lake sits in a deep rift valley surrounded by mountain ranges. These mountains shape airflow in complex ways. Cold air masses descending from higher elevations accelerate as they funnel toward the basin. Temperature gradients between water and land amplify pressure differences. The result is a set of localized wind systems that can strengthen rapidly with relatively little warning. Some winds even have local names, reflecting how consistently they occur. The summer wind, for example, descends from a valley on the western shore. It can begin suddenly and intensify to gale force within a short time. Researchers working on the lake watch forecasts carefully, yet localized conditions sometimes evolve faster than regional weather models predict. Wave formation on Baikal reflects this rapid wind intensification. Because the lake stretches more than 600 kilometers in length, winds blowing along its long axis generate significant fetch. Fetch refers to the uninterrupted distance over which wind travels across water. Longer fetch allows waves to build height and energy. Under strong winds, waves on Baikal can reach several meters, conditions more typical of coastal seas than inland lakes. For research vessels, these conditions affect scheduling immediately. Equipment deployment often requires calm water. Lowering sensitive instruments over the side of a pitching vessel increases risk of damage. Retrieving deployed arrays becomes difficult when waves obscure precise positioning. Even routine sampling may be postponed until conditions stabilize. Weather changes also influence safety planning. Sudden storms reduce visibility, complicating navigation. Fog occasionally develops when warm air passes over colder water, further reducing visual reference points. Radar assists navigation, but smaller craft still exercise caution under such conditions. Temperature shifts accompanying storms matter as well. Cold fronts moving across Siberia can drop air temperatures quickly. Crew members working on deck face exposure risk. Equipment exposed to cold air while partially wet from lake spray may ice over, affecting functionality. Wind-driven mixing affects the lake itself, not just surface operations. Strong winds push surface water toward one shore, causing upwelling of deeper, colder water elsewhere. This vertical mixing influences nutrient distribution and oxygen transport. Monitoring such events contributes to understanding ecological dynamics. Storm-induced mixing sometimes disrupts stratification layers built during calmer periods. Temperature profiles measured before and after storms often show noticeable changes. These changes ripple through biological communities dependent on stable environmental conditions. Acoustic monitoring during storms captures increased background noise from wave action. This noise complicates detection of biological sounds or subtle seismic signals. Researchers account for these variations when analysing long-term acoustic data sets. Satellite imagery helps track storm development across the lake, High-resolution weather satellites monitor cloud patterns, wind speed estimates, and surface temperature variations. Combining satellite data with local meteorological stations improves forecasting accuracy. Even with improved forecasting, sudden localized wind events remain challenging. Terrain-induced turbulence can produce wind gusts not predicted by broader models. Field teams therefore maintain flexible schedules and contingency plans. Winter storms introduce additional complications. Wind blowing across ice surfaces generates drifting snow, reducing visibility. Snow accumulation insulates ice unevenly, influencing thickness patterns. Pressure ridges may grow larger under sustained wind stress. Ice movement under storm conditions produces distinctive acoustic signatures. Monitoring these sounds helps assess structural changes in ice cover, informing safety decisions for winter expeditions. Hydrological impacts of storms extend beyond surface mixing. Heavy precipitation associated with certain weather systems increases tributary inflow. River discharge carries sediment and nutrients into the lake, temporarily altering water chemistry near inflow zones. Sediment plumes from strong winds can reduce water clarity in shallow areas. Resuspended particles scatter light, affecting both biological productivity and visual exploration efforts. Researchers sometimes observe short-term clarity reductions following storm events. Human infrastructure around Baikal must account for these weather patterns. Ports, research stations, and shoreline facilities incorporate design features to withstand strong winds and wave action. Mooring systems for research vessels require reinforcement. Tourism operators adjust schedules around weather forecasts as well. Boat excursions, diving activities, and shoreline visits depend on stable conditions. Safety considerations take priority when wind forecasts indicate potential rapid changes. For long-term ecological studies, storm frequency and intensity data provide valuable climate indicators. Changes in wind patterns may signal broader atmospheric shifts. Continuous meteorological monitoring supports climate modelling efforts. Historical records from local communities complement instrumental data. Generations living around the lake have observed seasonal wind behaviours. Integrating traditional knowledge with scientific measurement enriches understanding of local climate dynamics. Storm impacts extend into biological systems. Surface turbulence can redistribute plankton populations. Fish feeding patterns adjust to altered visibility and current structures. Seals may seek sheltered areas during rough conditions. Hydrothermal vent zones at depth experience minimal direct impact from surface storms, but vertical mixing events may influence chemical gradients over time. Understanding these interactions requires integrating meteorological and geological data sets. Exploration technology must tolerate rough conditions. Vessel stabilization systems, reinforced instrument housings, and flexible deployment protocols help maintain research continuity despite weather variability. Autonomous monitoring stations deployed in the lake continue collecting data through storms. These datasets provide valuable continuous records that human-operated missions might miss due to safety restrictions. Storm-driven wave action also influences shoreline erosion. Sediment transport patterns change gradually under repeated storm events. Geological surveys track these changes to understand long-term landscape evolution. Communication systems remain critical during severe weather. Satellite communication ensures coordination between field teams and research institutions. Redundant communication channels reduce risk during unexpected conditions. Even after storms pass, residual swell may persist. Calm skies do not always indicate immediate safe operating conditions. Researchers evaluate both wind forecasts and wave decay patterns before resuming certain activities. Understanding Baikal's wind and storm dynamics underscores why exploration cannot rely solely on predictable seasonal windows. Environmental variability demands adaptability and patience, and once atmospheric influences on the surface are considered, attention naturally shifts back below the waterline. because the same geological forces shaping the lake's basin continue to act beneath it, occasionally producing seismic activity that further complicates efforts to map and study the shifting floor beneath the water. If you imagine the bottom of a lake, the image that usually comes to mind is something stable: mud, sand, perhaps rocks, all resting quietly beneath the water. A place where time feels slow and change almost invisible. That expectation works reasonably well for many lakes formed by glaciers or river basins. Lake Baikal, however, rests on something far less settled. Beneath its immense volume of cold fresh water lies a tectonic rift that is still active, still widening, still adjusting. The lake floor is not a fixed stage. It is part of a geological process unfolding gradually but continuously. Fault lines cross the basin. Sediment layers shift. Seismic tremors ripple through the region. These movements are often subtle, detectable only by sensitive instruments, yet they remind researchers that Baikal is not merely deep. It is geologically alive. Seismic monitoring around the lake records hundreds of small earthquakes each year. Most are minor enough that people nearby do not notice them. Instruments do. Hydrophones placed underwater detect vibrations travelling through the basin. Seismographs along the shoreline register ground motion. Together, these datasets map stress patterns within the Earth's crust beneath the lake. These tremors influence sediment stability. Over time, repeated shaking can loosen accumulated material along underwater slopes. Eventually, gravity takes over. Sediment slides downward in what researchers call submarine landslides. These events redistribute vast amounts of material across the lake floor. Unlike landslides on land, underwater slides often occur unseen. There is no dust cloud, no visible debris cascade. Instead, acoustic sensors detect unusual vibrations. Water turbidity may increase temporarily as fine particles suspend in the water column. Later, sonar mapping reveals altered terrain where slopes once appeared stable. Such changes complicate long-term mapping efforts. A bathymetric survey conducted one decade may not perfectly match measurements taken decades later. Most differences are small, but cumulatively they reflect ongoing geological adjustment. Sediment accumulation in Baikal is remarkable in its thickness. In some areas, layers exceed 7 kilometers. These layers formed gradually as rivers carried minerals, organic matter, volcanic ash, and microscopic biological remains into the basin over millions of years. Each layer tells part of a climatic and geological story. Extracting sediment cores from such depths requires precision drilling equipment. Researchers lower specialized coring devices thousands of meters, penetrate sediment layers, and retrieve cylindrical samples. These cores reveal changes in climate, vegetation, volcanic activity, and even atmospheric chemistry across geological time. However, sediment cores also reveal disturbances. Fault displacement sometimes interrupts otherwise orderly layering. Earthquakes tilt strata. Submarine slides mix previously distinct layers. Interpreting these records demands careful analysis. Hydrothermal activity contributes further complexity. Beneath certain regions of the lake floor, geothermal heat interacts with groundwater. This interaction produces hydrothermal vents, releasing mineral-rich water into the lake. These vents alter local chemistry and support specialized microbial ecosystems. Mapping hydrothermal zones involves thermal sensors, chemical sampling, and high-resolution sonar imaging. Vent fields may shift over time as tectonic stress redistributes fractures in underlying rock. Continuous monitoring helps track these changes. Gas release from sediments represents another dynamic element. Methane produced by microbial decomposition sometimes accumulates beneath sediment layers. Tectonic disturbances or pressure changes can release this gas into the water column. Occasionally, methane bubbles become trapped in winter ice, creating visible patterns on the frozen surface. Understanding methane dynamics has climate relevance. Methane is a potent greenhouse gas. Studying its production and release in Baikal contributes to broader knowledge of natural methane sources. Geodetic measurements provide insight into how the basin itself moves over time. GPS stations around Baikal detect minute crustal shifts, often measured in millimeters per year. These measurements confirm that the rift continues to widen gradually. From a geological perspective, Baikal represents an early stage in continental rifting. Some scientists compare it with the East African Rift, where similar processes may eventually produce a new ocean basin. Whether Baikal will evolve similarly remains uncertain, but the ongoing stretching of the crust is well documented. This active geological setting influences exploration logistics. Deploying long-term instruments on the lake floor requires accounting for potential movement. Anchoring systems must accommodate subtle shifts. Instrument housings must withstand occasional seismic vibration. Acoustic positioning systems help track instrument location over time. If an array moves slightly due to sediment shifting or tectonic activity, researchers can detect displacement and adjust mapping data accordingly. ROV navigation near steep slopes demands caution. Unstable sediment can collapse if disturbed by thruster wash. Operators maintain distance to avoid triggering minor slides that could obscure visibility or damage equipment. Geological activity also affects biological habitats. Areas near hydrothermal vents support distinct microbial communities. Fault scarps create varied substrate types, influencing species distribution. Thus, geology and biology intertwine closely. Water chemistry near active geological zones sometimes differs from surrounding regions. Dissolved mineral concentrations vary. Temperature anomalies, though modest compared with oceanic vents, still influence local ecosystems. Seismic surveys using controlled acoustic sources help map subsurface structures. Reflected sound waves reveal layering patterns beneath the lake floor. Interpreting these patterns provides insight into rift evolution and sediment accumulation history. Such surveys require careful environmental assessment. Acoustic energy can influence wildlife. Protocols minimize ecological disturbance while achieving necessary data resolution. Long-term geological observation programs aim to understand whether seismic activity patterns are changing. Correlating tremor frequency with climatic factors, water level changes, or regional tectonic stress remains an active research area. Historical records indicate occasional stronger earthquakes in the region. These events remind local communities and researchers alike that tectonic forces, while often subtle, can manifest more dramatically. Infrastructure planning around Baikal incorporates seismic risk assessment. Buildings, pipelines, and research facilities consider potential ground movement. Understanding the shifting floor has practical implications beyond scientific curiosity. Underwater photography occasionally captures exposed rock faces along fault zones. These images reveal striations and fracture patterns indicative of tectonic movement. Comparing photographs across years helps detect gradual change. Sediment transport processes also influence nutrient cycling. Organic matter buried in sediments may later resurface through geological disturbance. This recycling affects deep-water biological communities. Seasonal temperature changes at the surface do not penetrate deeply enough to influence tectonic processes directly. Yet water level fluctuations can alter pressure distribution slightly. Researchers investigate whether such changes correlate with seismic activity patterns. Geological modelling integrates seismic data, sediment cores, geodetic measurements, and bathymetric surveys. These models aim to predict long-term basin evolution, though uncertainties remain due to the complexity of interacting factors. Public perception often focuses on Baikal's scenic surface, rather than its dynamic subsurface geology. Educational outreach highlighting tectonic activity enhances appreciation for the lake as a living geological system. Technological advances continue improving measurement precision. Fiber optic seismic sensors, high-resolution sonar arrays, and satellite geodesy all contribute to increasingly detailed understanding. Yet even with sophisticated tools, the fundamental reality persists. Baikal's floor is not static. It adjusts slowly but continuously. Exploration therefore captures snapshots within an evolving landscape rather than documenting a fixed environment, and recognizing that geological change beneath the lake continues to shape its structure naturally leads toward considering how human technology attempts to keep pace with these conditions. Because the deeper researchers look, the clearer it becomes that even advanced instruments encounter limits when confronting Baikal's depth, cold, and geological activity. If you listen to conversations about exploration in the modern world, there is often an assumption that technology eventually solves everything. Satellites map forests, robots explore Mars, deep-sea submersibles descend into ocean trenches. The narrative suggests steady progress toward complete understanding, and yet Lake Baikal quietly reminds researchers that even very capable technology encounters boundaries that are not always easy to overcome. It is not that instruments fail entirely. Sonar works, submersibles descend, sensors collect data, cameras record images. But operating consistently in Baikal's particular combination of depth, cold, geological activity, and vast scale means every technological solution introduces its own constraints. Exploration becomes a balance between capability and limitation, rather than a simple march toward total coverage. Pressure remains one of the most immediate challenges. Equipment descending toward Baikal's deepest points must withstand over 160 atmospheres of pressure. That force acts continuously on housings, seals, connectors, and sensor membranes. Even minor imperfections can become critical under sustained stress. Engineers design pressure-resistant casings using specialized alloys, ceramics and polymers, yet long-term reliability always requires monitoring. Cold compounds pressure-related issues. Materials behave differently at near-freezing temperatures. Some metals become more brittle, plastics lose flexibility, seal integrity changes subtly. Lubricants thicken, increasing friction in moving components. Batteries deliver reduced output. Each of these factors may seem manageable individually, but together they create an environment where maintenance intervals shorten and redundancy becomes essential. Power supply is a persistent limitation. Autonomous underwater vehicles rely on battery capacity. Cold water reduces battery efficiency, limiting operational duration. Adding insulation or heating systems helps, but heating consumes additional energy. Tethered vehicles solve some power issues by drawing electricity from surface vessels, yet tethers restrict maneuverability and introduce entanglement risk along uneven lake floor terrain. Communication underwater presents another boundary. Radio waves attenuate quickly in water, especially freshwater. Acoustic communication provides an alternative, but bandwidth remains limited. High-resolution video streams require tethered connections. Autonomous vehicles operating without tethers must store data internally until retrieval, delaying analysis and complicating real-time decision-making. Navigation accuracy decreases with depth as well. GPS signals do not penetrate water. Submersibles rely on inertial navigation systems, Doppler velocity logs, acoustic beacons, and sonar mapping. These systems accumulate small errors over time. Long missions require periodic recalibration to maintain positional accuracy. Visibility limitations, discussed earlier, mean that even advanced camera systems only reveal what artificial lighting reaches. Sonar mapping covers larger areas, but sonar imagery lacks the fine detail visual observation provides. Combining both approaches helps, yet full high-resolution visual coverage of the entire lake floor remains impractical. Instrument deployment logistics also impose limits. Transporting heavy research equipment into remote Siberian regions requires careful planning. Seasonal access windows constrain shipping schedules. Winter ice may block certain routes. Summer storms delay vessel operations. Even the best equipment cannot function if it cannot reach the lake reliably. Data management presents its own challenges. Modern instruments generate enormous volumes of information, video footage, acoustic records, chemical measurements, temperature profiles, genetic sequencing data. Processing, storing, and analysing these datasets require significant computational resources. Integrating results across disciplines adds further complexity. Long-term monitoring systems must operate unattended for extended periods. Sensors deployed on the lake floor or within the water column may remain in place for months or years. Designing equipment capable of reliable autonomous operation under pressure, cold, and occasional seismic disturbance is an ongoing engineering effort. Maintenance cycles depend heavily on seasonal conditions. Retrieving equipment during harsh winter weather or heavy summer storms may not be feasible. If a sensor malfunctions outside accessible windows, data gaps occur. Redundant systems mitigate risk but increase cost and logistical complexity. Cost itself becomes a limiting factor. Deepwater research equipment, submersibles, support vessels, and specialized sensors require substantial funding. International collaboration often helps distribute financial burden, yet sustained investment remains necessary for long-term projects. Environmental protection considerations introduce additional constraints. Researchers aim to minimize ecological disturbance. Equipment placement, sampling techniques, and acoustic survey protocols must balance scientific objectives with conservation priorities. This sometimes limits operational intensity or frequency. Technological solutions occasionally reveal new problems. Higher resolution sensors detect subtle variations previously unnoticed. Interpreting these variations requires new theoretical frameworks and additional measurements. Progress generates further questions rather than final answers. Software and data analysis tools evolve alongside hardware. Machine learning algorithms assist in identifying species from video footage, mapping geological features, and predicting environmental trends. Yet algorithm accuracy depends on training data quality. Limited datasets from extreme environments constrain model reliability. Human expertise remains essential despite automation advances. Skilled operators interpret sonar images, maintain equipment, and adapt field strategies in response to unexpected conditions. Training new specialists takes time, and field experience in Baikal's environment cannot be fully replicated elsewhere. Weather forecasting technology has improved significantly, yet localized wind systems around Baikal still produce surprises. Satellite data, atmospheric models, and local meteorological stations provide valuable information, but sudden wind events continue to influence operational planning. Remote sensing from satellites offers surface insights only. Ice cover, surface temperature, and turbidity patterns are visible from orbit. Deepwater processes remain inaccessible to satellite observation. Ground-based instrumentation remains indispensable. Technological progress does expand capabilities gradually. Battery chemistry improves. Material science develops more resilient components. Sensor sensitivity increases. Data transmission techniques evolve. Each advancement reduces certain limitations while revealing others. International research collaborations contribute technological diversity. Different institutions bring distinct equipment, methodologies, and analytical approaches. Sharing resources accelerates learning and helps overcome individual institutional constraints. Public interest sometimes drives technological investment. Media attention on Baikal's unique status encourages funding for research initiatives. Educational outreach helps maintain awareness of the lake's scientific importance. Despite all these efforts, the concept of complete exploration remains elusive. Technology enables deeper observation, more precise measurement, and broader coverage. Yet the lake's scale, environmental conditions, and ongoing geological activity ensure that absolute completeness stays beyond immediate reach. Researchers increasingly frame their goals in terms of continuous understanding rather than final mapping. Monitoring trends, detecting changes, refining models, and preserving ecological balance become central objectives. This perspective acknowledges that natural systems evolve, geological processes continue, biological communities adapt, climate influences shift conditions gradually. Technology supports observation within this dynamic context rather than conquering it definitively. And once the limits of technology become clear, the next challenge emerges naturally, because even with advanced instruments operating reliably, the sheer size of Lake Baikal introduces another obstacle that complicates attempts to map, monitor, and fully comprehend such an immense freshwater system. When people look at a map of Lake Baikal for the first time, they often register its length and think they understand its size. 636 kilometers from north to south sounds large, certainly. But maps compress distance, they flatten depth, they hide volume behind thin blue shapes. The true scale of Baikal only becomes clear when you begin to measure what it would take to study it thoroughly, point by point, layer by layer, season by season. Scale is not only about distance across the surface, it is about depth, volume, time, and variability. Baikal stretches more than 70 kilometers wide in places. It plunges more than 1,600 meters downward. It contains over 23,000 cubic kilometers of water. Each of those dimensions multiplies the complexity of exploration. Consider mapping alone. A high-resolution bathymetric survey of a small lake might take days or weeks. For Baikal, complete high-resolution coverage across the entire basin requires years of coordinated missions. Sonar systems sweep back and forth across enormous stretches of water, but even efficient grid patterns accumulate slowly when distances are measured in hundreds of kilometers. And mapping once is not enough. Sediment shifts, minor tectonic adjustments occur, underwater landslides alter slopes, new hydrothermal features may emerge. Updating maps to account for changes requires repeated surveys. Each pass adds clarity while also revealing new anomalies demanding further investigation. Vertical scale complicates matters further. Sampling at one depth tells only part of the story. Temperature, oxygen, concentration, nutrient levels, and biological communities vary across depth gradients. A comprehensive profile requires measurements taken at multiple depths at numerous horizontal locations. Multiply that by seasonal cycles, and the dataset expands rapidly. Seasonal variability alone demands year-round monitoring. Summer conditions differ from winter under ice. Spring mixing events redistribute nutrients and oxygen. Autumn cooling alters stratification. Capturing these shifts across such a vast basin requires sustained effort. The lake's three distinct basins, northern, central and southern, add another layer of scale complexity. Each basin differs slightly in depth, sediment composition and hydrodynamic behaviour. Treating Baikal as a uniform system risks oversimplification. Each region requires targeted study. Tributary inputs further expand the spatial scale. More than 300 rivers and streams feed into the lake. Monitoring their inflows means extending research beyond the main water body into surrounding watersheds. Land use changes, precipitation patterns, and sediment loads influence lake conditions indirectly but significantly. Even the shoreline length challenges comprehensive study. Thousands of kilometers of coastline include rocky cliffs, sandy beaches, wetlands, and human settlements. Each segment interacts differently with wave action, erosion, and ecological processes. Surveying shoreline changes across decades involves extensive fieldwork and satellite analysis. The sheer volume of water means that chemical changes distribute slowly. Detecting subtle shifts in nutrient concentration or contaminant levels requires precise measurement across large sample sets. Small variations may hold ecological significance, but can be statistically masked without adequate spatial coverage. Acoustic monitoring for seismic activity across the entire basin requires distributed sensor networks. Installing and maintaining these networks across deep and shallow zones takes coordination and resources. Data integration from widely spaced stations becomes a logistical project in itself. Biological scale presents its own challenge. Hundreds of endemic species occupy various niches across depths and regions. Documenting species distribution requires repeated sampling across multiple sites. Rare species may inhabit only small geographic pockets, making detection dependent on sampling density. Genetic studies expand the scale further. Environmental DNA collected from water samples must represent different regions and depths to capture biodiversity accurately. Sampling too sparsely risks missing localized populations. Technological resources are finite. Research vessels can cover only so much territory within operational windows. Autonomous vehicles have limited endurance. Budget constraints determine how many missions can occur each year. Scale therefore interacts directly with funding and time. Time itself introduces another dimension of scale. Baikal has existed for millions of years. Climate cycles have come and gone. Geological processes continue. Understanding long-term trends requires decades of observation at minimum. No single research generation completes the task. Climate change amplifies scale challenges. Detecting gradual warming or shifts in ice duration demands long data sets. Distinguishing natural variability from anthropogenic influence requires careful statistical analysis across extended timeframes. Public perception often underestimates scale because scenic imagery captures only small portions of the lake. A photograph of clear water and distant mountains cannot convey the full, three-dimensional extent beneath. From an operational standpoint, fuel logistics for vessels traversing hundreds of kilometers add complexity. Equipment must withstand travel across open stretches where safe harbor may be distant. Weather patterns vary along the lake's length, meaning conditions in the northern basin may differ from those in the south simultaneously. Data management scales accordingly. High-resolution sonar surveys generate terabytes of information. Continuous monitoring sensors produce long time series datasets. Integrating physical, chemical, biological, and geological data requires robust computational infrastructure. Interdisciplinary collaboration helps address scale but introduces coordination challenges. Limnologists, geologists, climatologists, and engineers must align methodologies. Data standardization ensures comparability across teams. Remote sensing offers partial assistance for surface conditions. Satellite imagery provides lake-wide snapshots of ice cover and surface temperature. Yet subsurface processes remain largely invisible from orbit, requiring direct sampling. Longitudinal studies across decades depend on consistent measurement protocols. Instrument upgrades risk introducing calibration differences. Maintaining methodological continuity becomes critical when tracking subtle changes across large spatial scales. Scale also influences conservation planning. Protecting endemic species across such an extensive habitat requires region-specific strategies. Enforcement of environmental regulations must consider remote stretches with limited oversight. Educational outreach struggles to communicate scale effectively. Explaining why a lake cannot be fully explored sometimes meets skepticism until volume and area figures are contextualized properly. Even tourism reflects scale challenges. Managing visitor impact across widespread shoreline communities requires coordinated policy rather than isolated measures. Mapping underwater topography at meter-scale resolution across thousands of square kilometers remains technically possible, but resource-intensive. Prioritization becomes necessary. Scientists select representative areas while acknowledging incomplete coverage elsewhere. The concept of representativeness introduces uncertainty. Can selected sampling sites accurately reflect broader conditions? Statistical sampling designs attempt to address this, yet natural variability complicates assumptions. Hydrological modelling across the basin requires integrating wind patterns, basin morphology, inflow rates, and thermal gradients. Each model iteration improves predictive capacity but still relies on approximations. In large systems, rare events matter. A single significant underwater landslide may alter local ecosystems. An unusual algal bloom may signal broader change. Detecting such events across vast space demands continuous observation. Scale therefore acts as both physical and conceptual boundary. It stretches resources, time and attention. It ensures that exploration remains iterative rather than final. And once the magnitude of Baikal's dimensions becomes clear, it naturally leads toward considering how human perception interacts with that magnitude. Because even with maps, models, and measurements, understanding such a vast system requires confronting the limits not only of equipment, but also of how we interpret what exploration truly means. If you spend enough time studying a place as vast and unusual as Lake Baikal, you eventually notice something interesting that has nothing to do with sonar readings or sediment cores. Alongside the scientific data, stories persist. Some are old, some evolve over time, some reflect fear, respect, or curiosity. Others simply try to explain what feels difficult to explain. And around Baikal, those stories have accumulated for centuries, sometimes quietly, sometimes vividly. This does not happen because people lack scientific understanding. It happens because environments that resist easy explanation often invite narrative alongside measurement. A lake that is older than most landscapes around it, deeper than typical inland waters, and capable of sudden weather shifts naturally inspires interpretation beyond charts and instruments. Indigenous communities around Baikal have long regarded the lake as more than a geographic feature. Among the Buryat people, traditional beliefs often frame Baikal as a powerful living presence. Rituals acknowledging the lake's significance were historically common, reflecting a relationship built on dependence, observation, and respect rather than conquest. Stories about spirits inhabiting the lake's depths circulated long before modern exploration equipment existed. These narratives often served practical purposes, warning against venturing onto unstable ice, encouraging caution during storms, reinforcing sustainable fishing practices. Cultural storytelling sometimes functioned as environmental guidance encoded in memorable form. One frequently mentioned figure in regional folklore is a water spirit sometimes described as the Master of Baikal. Accounts vary widely, as oral traditions tend to adapt across generations. Some portray this presence as protective, ensuring balance between humans and nature. Others frame it as unpredictable, reflecting the lake's sudden storms and shifting ice. From a scientific perspective, such stories do not conflict with empirical observation. They reflect human attempts to interpret powerful natural systems before instruments provided detailed measurements. Even today, scientific knowledge coexists with cultural interpretation. Early explorers arriving from outside the region recorded local accounts with a mixture of curiosity and skepticism. Travel diaries from the 19th century include references to unusual sounds under the ice, sudden fog banks, or unexplained lights on the water. Modern science offers explanations for many of these observations, yet the narratives remain part of regional identity. Ice acoustics provide a good example. The booming sounds produced by thermal stress in winter ice sheets can travel long distances. Before acoustic monitoring explained these phenomena, they easily became associated with unseen forces. Even now, hearing those sounds without prior explanation can feel unsettling. Methane bubbles trapped in winter ice have also inspired speculation historically. Clear ice sometimes reveals circular patterns of frozen gas pockets. Without chemical analysis, these patterns appeared mysterious. Today, researchers study methane release as part of climate and geological research, yet the visual effect continues to spark curiosity. Occasional reports of unusual creatures surface in popular media. Large fish sightings, unexpected seal behaviour, or ambiguous sonar images sometimes fuel speculation about unknown species. Scientific surveys have catalogued most large fauna, yet incomplete coverage across such a vast system leaves room for continued investigation. These reports rarely indicate entirely unknown large species. More often, they reflect misidentification, unusual environmental conditions affecting visibility, or natural variation within known populations. Still, the persistence of such stories demonstrates how mystery accompanies scale. Scientific exploration occasionally contributes unintentionally to myth formation. Early deep-water sonar surveys produced images difficult for non-specialists to interpret. Media interpretation sometimes exaggerated ambiguity, reinforcing perceptions of hidden unknowns beneath the surface. Clear communication helps address such misconceptions, explaining how sonar works, how biological surveys operate, and how data interpretation occurs reduces unnecessary speculation while preserving curiosity. Cultural tourism around Baikal sometimes incorporates folklore. Guided tours may include traditional stories alongside geological explanations. This blended narrative acknowledges both scientific knowledge and historical cultural perspectives. Local artists, writers, and musicians draw inspiration from the lake's reputation. Creative interpretation reinforces cultural continuity while attracting broader public interest in the region. Environmental conservation efforts occasionally reference traditional respect for the lake. Framing protection as continuity with historical stewardship resonates culturally and supports policy acceptance. Educational programs in surrounding communities often present both scientific understanding and folklore context. Students learn geological formation processes alongside traditional narratives. This dual approach fosters appreciation without dismissing cultural heritage. Scientific researchers working in the region frequently engage with the local communities. Respectful dialogue enhances collaboration and supports field logistics. Cultural awareness improves research outcomes as well as community relationships. Language itself carries traces of historical interpretation. Place names around the lake sometimes reflect descriptive observations or traditional beliefs. Linguistic study complements archaeological and ethnographic research. Archaeological evidence indicates human presence around Baikal for thousands of years. Tools, settlement remains, and burial sites provide insight into how earlier populations interacted with the lake. Oral traditions often preserve environmental knowledge consistent with archaeological findings. Modern scientific explanation does not erase earlier narratives, it contextualizes them. For example, understanding tectonic activity explains certain environmental behaviors once attributed solely to supernatural forces. Yet cultural memory of those behaviors remains valuable. Media portrayals sometimes amplify mystery for dramatic effect. Documentaries highlighting Baikal's uniqueness occasionally emphasize unexplored depths or rare species discoveries. While factually grounded, presentation style can shape public perception toward intrigue. Researchers themselves sometimes describe Baikal with language reflecting respect, rather than purely technical characterization. Terms like living system or dynamic basin convey scientific reality while acknowledging complexity. The coexistence of myth and science around Baikal illustrates a broader human pattern. Places that challenge understanding inspire layered interpretation. Scientific progress adds detail without eliminating narrative interest. In practical exploration terms, folklore occasionally influences public response to research initiatives. Clear communication helps maintain trust and encourages community support for scientific work. Cultural festivals around Baikal sometimes celebrate both natural beauty and traditional stories. These events contribute to regional identity while promoting environmental awareness. Documentation of oral traditions remains important as older generations pass knowledge to younger ones. Anthropological research preserves these narratives alongside ecological data. The persistence of stories does not imply ignorance. It reflects a human tendency to frame complex environments through both measurement and meaning. And once cultural interpretation is considered alongside scientific observation, attention naturally turns toward how human presence itself interacts with the lake. Because respecting Baikal's cultural and ecological significance also involves recognizing how modern activity influences the fragile systems that have persisted there for millions of years. When people talk about exploration, the conversation often leans toward capability. What tools do we have? How deep can we go? How much data can we collect? But with Lake Baikal, another dimension quietly shapes the discussion. Not everything that can be explored necessarily should be explored without restraint. Around this lake especially, cultural memory, environmental responsibility, and simple practical limits combine to form boundaries that are not always marked on maps. For thousands of years, human communities have lived around Baikal's shores. Archaeological findings show continuous habitation stretching back deep into prehistory. Tools, settlement remains, burial sites, and trade artifacts all indicate a long-standing relationship between people and the lake. That relationship was not built on extraction alone. It involved observation, adaptation, and a recognition that the lake's scale and unpredictability demanded respect. Among the Buryat people and other indigenous groups of the region, Baikal traditionally holds spiritual significance. Historical accounts describe offerings made near the water's edge, ceremonies acknowledging the lake's importance, and cultural narratives framing Baikal as a powerful presence rather than a passive resource. These practices were not abstract symbolism. They shaped behaviour. Fishing practices remained seasonal and restrained. Travel across ice followed established knowledge passed through generations. Modern scientific exploration enters this cultural landscape with increasing awareness. Researchers today often consult local communities before establishing long-term study sites. This consultation serves practical and ethical purposes. Local knowledge can improve safety planning. Cultural awareness strengthens collaboration. Respectful engagement reduces misunderstandings that might otherwise complicate research. Human boundaries around Baikal also arise from environmental considerations. The lake contains roughly 1/5 of the world's unfrozen freshwater. That fact alone elevates its global ecological significance. Protecting water quality becomes not only a regional concern but a broader planetary one. Industrial development around Baikal has a complicated history. During the 20th century, certain industries operated along the shoreline, most notably pulp and paper production facilities. Environmental monitoring eventually revealed impacts on water chemistry and local ecosystems. Public concern, scientific evidence, and policy debate led to regulatory changes and eventual closure of some high-impact operations. Today, environmental regulation around Baikal reflects lessons learned. Strict protections govern wastewater discharge, shoreline construction, and resource extraction. Enforcement varies in effectiveness, as it does in many large regions, but the overall framework prioritizes preservation. Tourism introduces newer form of human pressure. Visitors arrive drawn by clear water, dramatic winter ice formations, and unique wildlife. Tourism supports local economies but also requires infrastructure, lodging, transportation, waste management. Managing visitor impact without degrading fragile ecosystems remains an ongoing challenge. Waste management is particularly critical. Even small pollution inputs can persist due to the lake's slow water turnover. Educational campaigns encourage responsible visitor behaviour. Local authorities invest in improved waste treatment facilities. Monitoring programs track nutrient and contaminant levels. Fishing practices illustrate another balance point. The omelfish has long been culturally and economically important. Overfishing concerns prompted temporary bans and quota adjustments. Scientific stock assessments guide policy decisions, though balancing livelihoods with conservation remains complex. Climate change adds a further dimension to human boundaries. Surface temperature increases, altered ice duration, and changing precipitation patterns influence both ecosystems and human activity. Adaptive management strategies rely on continuous scientific monitoring combined with community input. Transportation infrastructure around the lake has expanded gradually. Roads, rail lines, and ports facilitate access. While improved connectivity benefits research and local economies, it also increases potential environmental stress. Planning authorities weigh development needs against conservation priorities. Scientific exploration itself carries environmental responsibilities. Deploying instruments, collecting biological samples, and conducting acoustic surveys must minimize ecological disturbance. Ethical research protocols emphasize non-invasive techniques whenever possible. Education plays an essential role in maintaining human boundaries. Schools around Baikal incorporate environmental science into curricula. Students learn about water chemistry, biodiversity, and conservation alongside cultural history. This integrated approach fosters long-term stewardship. International organizations sometimes participate in conservation initiatives. UNESCO designated Lake Baikal as a World Heritage Site in 1996, recognizing both its ecological significance and need for protection. Such recognition increases global awareness while encouraging preservation policies. Hydroelectric development on the Angara River, the lake's primary outflow, illustrates another boundary consideration. Dams influence water level regulation, affecting shoreline ecosystems. Ongoing monitoring seeks to balance energy production with ecological stability. Local communities contribute observational knowledge valuable for research. Fishers notice shifts in species distribution. Residents observe changes in ice formation timing. Integrating these observations with scientific data enhances understanding. Economic realities inevitably influence boundary decisions. Communities depend on tourism, fishing, and limited industry. Conservation policies must consider livelihoods to remain sustainable. Collaborative planning helps align economic and environmental goals. Public perception of Baikal as pristine sometimes obscures existing challenges. Pollution incidents, invasive species risks, and climate impacts require ongoing attention. Transparency in reporting environmental data builds trust. Cultural festivals celebrating the lake often include conservation messaging. Art, music, and storytelling reinforce respect for the water. These cultural expressions support environmental awareness without formal regulation. Legal frameworks governing Baikal continue evolving. Environmental protection laws adapt as scientific understanding improves. Enforcement mechanisms strengthen gradually, though resource limitations persist. Scientific stations around the lake operate under environmental guidelines. Waste disposal, fuel storage, and equipment maintenance follow strict protocols. Research presence aims to minimize footprint while maximizing knowledge. The concept of sacred water does not necessarily conflict with scientific exploration. Instead, it introduces an additional perspective that knowledge acquisition carries responsibility. Recognizing cultural significance encourages careful methodology. Boundaries also exist simply because of human safety. Remote conditions, harsh weather, and logistical constraints limit continuous presence. Exploration schedules adapt to seasonal accessibility and safety considerations. Technological ambition sometimes meets ethical restraint. Just because deeper drilling or more intensive sampling is technically feasible does not mean it proceeds without evaluation. Environmental impact assessments guide decisions. Youth engagement initiatives encourage future stewardship. Student expeditions, citizen science programs, and community monitoring projects connect younger generations with the lake's health. Media coverage occasionally highlights conflicts between development proposals and conservation priorities. Public debate reflects the lake's importance across cultural, ecological, and economic dimensions. Academic research increasingly integrates social science perspectives. Understanding how communities perceive the lake informs policy design and communication strategies. As awareness grows globally about freshwater scarcity, Baikal's significance expands beyond regional identity. International interest supports funding for conservation research while raising geopolitical considerations about resource protection. And once the interplay between human respect, cultural heritage, and environmental protection becomes clear, attention naturally turns toward the more recent pressures placed on the lake. Because even with strong cultural boundaries and regulatory frameworks, modern pollution and ecological stress still test the resilience of this remarkably old freshwater system. Lake Baikal is often described as one of the purest large freshwater bodies on Earth. The clarity of its water reinforces that perception. In many places, stones and submerged logs remain visible far below the surface. Measurements of dissolved minerals show relatively low concentrations compared to many other lakes. Yet purity in environmental terms is never absolute. It is maintained through balance, and balance can shift. The idea of pollution at Baikal does not usually involve dramatic images of oil slicks or industrial discharge pipes visible from shore. Instead, it often manifests as gradual changes in nutrient levels, localized contamination, and emerging ecological stress that requires careful measurement to detect. Because the lake is so large and its water turnover so slow, even small inputs matter over long timescales. Historically, the most widely discussed source of concern was industrial activity along the southern shoreline. The Baikal pulp and paper mill, established in the mid-20th century, discharged treated wastewater into the lake for decades. Although treatment systems were upgraded over time, environmental monitoring revealed chemical impacts on surrounding water and sediment. Scientific studies examined concentrations of organic compounds, heavy metals, and nutrient loads near discharge sites. Elevated levels compared to baseline conditions prompted debate among policymakers, scientists, and local communities. Eventually, after years of scrutiny and public discussion, the facility ceased operations. The closure reduced one major industrial input, but it did not erase past effects entirely. Sediment cores collected near former discharge zones still show chemical signatures from that period. Analysing these layers helps researchers reconstruct pollution history and evaluate recovery trends. Over time, dilution and natural processes reduce contaminant concentrations, but slow water turnover means legacy effects persist longer than they might in smaller, faster-flushing systems. Urban wastewater represents another challenge. Growing tourism and expanding settlements increase demand for sewage treatment infrastructure. Inadequate facilities risk nutrient enrichment of nearshore waters. Elevated nutrient levels can stimulate algal growth, reducing clarity and altering oxygen dynamics. Monitoring programs measure phosphorus and nitrogen concentrations regularly. Even modest increases can shift ecological balance in certain shallow bays. In recent years, researchers have documented localized algal blooms in some areas where nutrient input from human activity appears elevated. Plastic pollution has also reached Baikal, as it has reached most aquatic systems globally. While large accumulations remain relatively limited compared to heavily industrialized regions, microplastic particles have been detected in water samples. These particles originate from consumer waste, synthetic clothing fibers, and degraded packaging. Studying microplastic distribution across such a large volume requires coordinated sampling across depths and regions. Researchers analyze sediment and water samples using filtration and spectroscopy techniques to quantify particle presence. Results so far suggest relatively low concentrations compared with many global lakes, yet the trend requires ongoing observation. Atmospheric deposition contributes contaminants as well. Pollutants released far from Baikal can travel through the atmosphere and settle into the watershed. Persistent organic pollutants and trace metals occasionally appear in monitoring data. Identifying their sources often involves international collaboration. Agricultural runoff from tributary watersheds introduces additional nutrients and sediment. While the surrounding region remains less densely farmed than many global basins, even small-scale land use changes can influence water chemistry locally. Monitoring tributary inflows helps identify emerging patterns. Climate change intersects with pollution concerns in subtle ways. Warmer surface temperatures can enhance biological activity, potentially amplifying the effects of nutrient input. Changes in ice cover duration may alter mixing patterns, influencing contaminant distribution. Oil transport infrastructure near parts of the watershed occasionally raises concerns about accidental spills. Strict regulations aim to prevent such incidents, yet risk management remains an ongoing priority given the lake's importance. Tourism waste management presents practical challenges. Remote campsites and seasonal visitor surges increase pressure on sanitation systems. Education campaigns encourage responsible disposal practices. Local authorities expand waste treatment capacity gradually to match demand. Scientific research itself maintains strict environmental protocols. Field stations manage fuel storage carefully. Waste generated during expeditions is removed rather than disposed of locally. Minimizing research footprint reinforces conservation principles. Biological indicators provide early warning signs of pollution. Changes in sponge health, shifts in plankton composition, or unusual mortality events among fish and seals can signal environmental stress. Continuous ecological monitoring supports rapid response when anomalies appear. In the early 2000s, reports emerged of declining sponge health in certain areas. Scientists investigated potential causes, including temperature shifts, nutrient increases, and pathogen presence. While multiple factors likely contributed, the episode underscored the lake's sensitivity to environmental change. Heavy metal analysis in fish tissues helps assess bioaccumulation risk. So far, levels remain within safe ranges for consumption in most monitored zones, but continued sampling ensures early detection of trends. The lake's World Heritage status increases international attention to environmental management. Reporting requirements encourage transparency in pollution monitoring and remediation efforts. Community engagement strengthens pollution prevention. Local organisations participate in shoreline cleanups, environmental education events, and citizen science initiatives. These efforts reinforce shared responsibility. Regulatory enforcement varies across jurisdictions, but overall policy direction emphasises preservation. Restrictions on industrial expansion near the shoreline reflect recognition of the lake's vulnerability. Technological improvements in wastewater treatment reduce nutrient input compared to past decades. Upgrading infrastructure remains expensive, yet long-term benefits justify investment. Sediment transport patterns influence pollutant distribution. Contaminants introduced near shore may settle locally or disperse gradually through currents. Understanding these pathways requires integrating hydrodynamic models with chemical data. While Baikal remains comparatively clean on a global scale, the phrase "edge of purity" captures the tension between protection and pressure. The lake's clarity does not guarantee immunity from impact. Public awareness campaigns emphasize the connection between daily behavior and lake health. Proper waste disposal, responsible tourism, and support for environmental regulation contribute cumulatively to preservation. International scientific collaboration strengthens pollution research capacity. Shared expertise in analytical chemistry, modelling, and ecological assessment enhances monitoring effectiveness. The concept of resilience applies cautiously. Baikal's size and volume provide buffering capacity against small disturbances. However, resilience has limits, particularly when multiple stresses interact. Future research priorities include microplastic trend analysis, climate pollution interaction studies, and continued sediment core examination to track long-term recovery patterns. And once the realities of modern environmental pressure are acknowledged, the conversation naturally shifts toward what has been discovered so far and what remains uncertain, because despite decades of study and careful monitoring, Lake Baikal continues to hold unanswered questions beneath its clear surface. After decades of research expeditions, sediment drilling campaigns, submersible descents, biological surveys, satellite monitoring, and climate modelling, it would be reasonable to expect that Lake Baikal now stands fully catalogued. There are thousands of scientific papers. International collaborations have operated for generations. Instruments have mapped large portions of the lake floor. Species lists grow longer every year. And yet the honest summary of Baikal today requires two parallel statements. We have found a great deal, and we have not found everything. Let's begin with what we do know. We know that Baikal is the oldest existing freshwater lake on Earth, approximately 25 million years old. Geological surveys confirm it sits within an active continental rift. Seismic monitoring demonstrates that the basin continues to widen gradually. Sediment cores extending kilometres beneath the lake floor reveal layered records of climate cycles, volcanic events, and regional ecological shifts stretching back millions of years. We know its depth precisely. Sonar mapping has established the maximum depth at just over 1,600 metres. We know its volume, around 23,600 cubic kilometres of fresh water. We know its shoreline length, its inflow and outflow systems, and the basic hydrodynamics governing seasonal mixing and stratification. We know that more than half of its species are endemic. Thousands of organisms have been described and classified, including unique amphipods, sponges, fish, and the freshwater seal. Genetic sequencing has revealed microbial diversity beyond what traditional sampling methods once suggested. We know many of the metabolic pathways allowing life to persist in near-freezing, oxygen-rich, deep water. We know that hydrothermal vents exist in certain deep zones. We have measured their chemical outputs. We have mapped fault lines along the lake floor. We have tracked methane release patterns and studied sediment accumulation rates. We know that surface water clarity remains exceptional in many areas. We monitor nutrient concentrations, oxygen profiles, and temperature gradients across seasons. We track ice formation and breakup dates. We document wind systems and storm frequency. We monitor pollution trends and have observed recovery following industrial closure. All of that knowledge is real, measurable, documented. And still there are gaps. For one thing, complete high-resolution mapping of the entire lake floor has not been achieved. Large sections have been surveyed, yes, but resolution varies. Some deep areas remain mapped only at coarse scale. Subtle geological features may exist undetected simply because no vehicle has passed directly over them with fine-resolution sonar. Biologically, new species continue to be described. Even in well-studied zones, genetic analysis sometimes reveals that what was once considered a single species is actually multiple distinct lineages. Microbial diversity especially remains incompletely characterized. Environmental DNA sampling expands detection capacity, yet interpretation requires caution. Behavioral ecology in deep zones remains partially understood. Cameras capture moments, but continuous observation across seasons at depth remains technically and logistically difficult. We do not yet possess uninterrupted long-duration visual records from the deepest regions. Hydrothermal systems are mapped only where surveys have specifically targeted them. It remains possible that additional vent fields exist in underexplored areas. Seismic data suggest complex subsurface structures that have not been directly imaged. Methane dynamics remain under active study. We know methane accumulates in sediments and sometimes becomes trapped in ice. We have measured concentrations. Yet long-term modelling of release patterns under climate change scenarios still carries uncertainty. Climate impacts introduce further unknowns. Surface warming trends have been recorded. Ice duration appears to be shifting gradually. But predicting how endemic deep-water species will respond to sustained temperature change requires decades of additional data. We know that nutrient increases in certain nearshore zones correlate with human activity. But disentangling the precise balance between local runoff, atmospheric deposition, and natural variability demands further monitoring. Water mixing patterns across the three main basins vary in subtle ways. Some models explain much of the observed behaviour, yet anomalies appear in certain years that do not fit established expectations. Refining hydrodynamic models continues to be a priority. The interaction between geological activity and biological systems remains partially understood. How frequently do small tremors reshape microhabitats? Do hydrothermal changes influence species distribution over time? Data exist, but comprehensive synthesis across disciplines remains ongoing. Even sediment cores, which extend back millions of years, leave questions. Certain abrupt transitions in the geological record suggest past climate events whose precise causes are still debated. Interpreting those layers requires integrating paleoclimate data from other regions of the world. From a technological standpoint, our tools are capable, but not omnipresent. Autonomous vehicles cannot patrol the entire lake continuously. Monitoring stations sample specific points, not every cubic kilometre. Data gaps remain inevitable in such a vast system. There are also epistemological limits. Some processes occur at scales too fine or too gradual to capture fully. Microbial interactions in sediment layers unfold over timescales longer than human observation programs. Geological change proceeds slowly but cumulatively. Public perception sometimes imagines unexplored zones as dramatic or mysterious in cinematic ways. In reality, unknowns often consist of incomplete data sets, unresolved statistical variation, or unverified ecological interactions. The mystery is subtle rather than sensational. We have not discovered enormous undiscovered megafauna hiding in the depths. Surveys make that unlikely, but we have not catalogued every microorganism. We have not mapped every metre of lake floor at identical resolution. We have not fully predicted the lake's response to accelerating global climate change. Scientific humility plays a role here. Each discovery clarifies certain aspects while revealing further complexity. A newly identified amphipod species leads to questions about its evolutionary origin. A refined temperature model prompts investigation into anomalous mixing events. Funding cycles influence what we have and have not found. Certain regions receive concentrated study during active projects. Others remain lower priority until new grants enable exploration. International collaboration broadens coverage, yet coordinating multi-year, basin-wide studies requires logistical alignment that is not always simple. Data integration across decades also presents challenges. Instrument calibration changes over time. Methodologies improve. Ensuring continuity across historical datasets demands careful cross-referencing. We have found enough to confirm that Baikal is extraordinary by any freshwater standard. We have not found enough to declare its study complete. And perhaps that is the more realistic understanding of exploration. Not a binary state of known versus unknown, but an evolving gradient where knowledge accumulates while uncertainty narrows gradually without disappearing entirely. Recognizing this leads naturally to a deeper reflection, because once it becomes clear that mapping, measuring, and cataloguing do not equate to total understanding, the idea of exploration itself begins to shift from conquest towards something more nuanced and ongoing. When most people hear the word exploration, the image that comes to mind usually involves completion. A blank map gradually filled in, unknown territory becoming known, a final report confirming that the last mystery has been solved. That narrative works well for certain situations. Survey a coastline, measure a mountain, catalogue a forest, and eventually the outlines become clear. With Lake Baikal, though, the idea of completion starts to blur. Exploration happens constantly, yet the sense of finishing never quite arrives. Part of this comes from how humans define knowing a place. We often assume that once we measure dimensions, identify species and map terrain, the job is essentially done. By that standard, Baikal might appear close to complete. Its depth is measured, its shoreline mapped, thousands of biological species documented, climate trends monitored, geological structures surveyed. On paper, the lake seems well described. But description is not the same as full understanding. Measurement provides data points. Understanding involves relationships among those points, how systems interact over time, how they respond to change. Baikal operates on spatial and temporal scales large enough that those relationships continue evolving, even while measurement improves. Take water chemistry as an example. Scientists can measure oxygen concentration at various depths with high precision. They can map seasonal variation. They can model circulation patterns. Yet predicting exactly how those patterns will shift under sustained climate warming remains uncertain. Exploration generates data, but interpretation continues. Biological knowledge follows a similar pattern. We have catalogued many endemic species. Genetic sequencing has expanded biodiversity awareness. Still, ecosystem interactions unfold over long time scales. Subtle shifts in plankton communities may cascade through food webs in ways only visible after years of monitoring. Geological activity reinforces the sense that exploration is ongoing rather than final. The rift beneath Baikal continues to widen slowly. Sediment accumulates. Fault lines adjust. Hydrothermal activity fluctuates. Mapping today captures a moment within a process that does not stop. Technology sometimes creates the impression of completeness. High-resolution sonar maps look detailed and definitive. Satellite imagery provides expansive surface coverage. Autonomous vehicles collect continuous data streams. Yet these tools sample selectively. They cover portions, not totality. Data visualization can also shape perception. When researchers publish comprehensive-looking charts or models, audiences may assume finality. In reality, models evolve continuously as new data arrives. Scientific language often emphasizes uncertainty margins, though those nuances may fade in public interpretation. Exploration historically carried connotations of conquest. Unknown territories were discovered, mapped, claimed. That framing does not translate neatly to complex ecological systems like Baikal. There is nothing to conquer in a lake that continues changing regardless of human observation. Instead, exploration becomes closer to monitoring. Scientists return repeatedly to similar sites, collecting updated measurements. Long-term datasets gain importance. Consistency sometimes matters more than novelty. This shift affects how success is defined. Rather than finishing exploration, researchers aim to improve resolution, reduce uncertainty, detect trends earlier, and understand interactions more deeply. Progress becomes incremental rather than terminal. Human psychology often prefers closure. A completed puzzle feels satisfying. An open-ended investigation requires patience. Baikal encourages that patience because its processes do not conform to short research cycles. Climate variability reinforces the illusion of exploration. As global conditions shift, baseline assumptions require revision. Temperature trends change mixing dynamics. Ice cover duration shifts. Biological responses follow. Exploration must adapt continuously. Public narratives sometimes emphasize mystery dramatically. Headlines about unexplored depths attract attention. Yet most unknowns involve complex data interpretation, rather than hidden dramatic discoveries. Communicating this nuance helps align expectations. Funding structures influence exploration framing as well. Grant proposals often emphasize new discovery. Long-term monitoring may receive less immediate excitement despite its scientific importance. Researchers balance both priorities. Educational outreach plays a role in reshaping perception. Teaching that exploration can mean sustained observation rather than single expeditions encourages more realistic understanding. Comparisons with ocean exploration illustrate the point. Oceans remain only partially mapped at high resolution, despite decades of effort. Baikal, though smaller, presents similar challenges scaled to freshwater conditions. Temporal scale remains central. Geological change operates over millions of years. Ecological change may span decades. Human research programs usually operate over years. Aligning these timescales requires continuity across generations of scientists. Technological optimism sometimes assumes future tools will eliminate all uncertainty. While advancements expand capability, natural variability ensures some unpredictability persists. measurement precision improves faster than environmental stability. Exploration also involves interpretation frameworks. New theories reshape how existing data is understood. A dataset collected decades ago may gain new significance under updated analytical models. Cultural perspectives influence exploration narratives too. Indigenous communities historically approached Baikal as a living system rather than an object to be fully known. Modern science increasingly echoes that relational perspective. The illusion of exploration does not mean exploration lacks value. On the contrary, continuous study improves environmental stewardship, informs policy, and deepens appreciation for complex natural systems. Recognizing limits encourages humility. It reminds researchers and the public alike that knowledge accumulation does not equate to absolute control or prediction. Technological capability should therefore be paired with cautious interpretation. Instruments reveal patterns. Nature retains variability. This understanding influences conservation policy. Managing Baikal effectively requires adaptive approaches, acknowledging uncertainty rather than assuming fixed conditions. Scientific communication evolves accordingly. Instead of presenting final answers, researchers emphasize confidence ranges, ongoing monitoring needs, and collaborative inquiry. Even tourism narratives shift gradually. Rather than promoting Baikal as a fully known destination, educational materials increasingly highlight its dynamic nature. Students entering limnology, geology, or climate science often encounter Baikal as a case study in complexity. It demonstrates how measurement, modelling, and monitoring intersect. Over time, this reframing of exploration becomes less about discovering what exists and more about understanding how it changes, and once exploration is understood in that ongoing sense, the lake itself begins to feel less like a puzzle awaiting completion and more like a system whose defining feature may be its ability to retain elements of mystery even as knowledge steadily accumulates. When you place together everything we have discussed, the depth, the cold, the pressure, the storms, the shifting tectonic floor, the biological uniqueness, the cultural reverence, the pollution risks, the technological constraints, the vast scale, a pattern becomes clear. Lake Baikal is not unexplored in the sense of being untouched by science. It has been measured, mapped, sampled, modelled, and monitored for decades. And yet, despite all of that effort, it does not feel fully revealed. That is not because there is a single dramatic secret waiting at the bottom. It is because the lake's nature resists total capture, not through intention, not through mystery in a cinematic sense, but through complexity layered across space and time. Baikal's water column alone represents an enormous vertical system. Surface conditions shift with weather and seasons. Mid-depth layers respond to stratification and mixing cycles. Deep zones remain cold and dark, stable but not static. Each layer interacts with the others, sometimes subtly, sometimes abruptly. No single expedition can observe all of it at once. The geological basin beneath the water continues to evolve. Fault lines adjust, sediment accumulates, hydrothermal activity fluctuates. Even if every square metre were mapped today at the highest possible resolution, that map would begin aging immediately. Geological time does not pause while data is processed. Biological systems add another dimension. Endemic species adapt to slow environmental change. Microbial communities shift in response to nutrient gradients. Subtle temperature increases alter reproductive timing. Detecting these changes requires long-term observation, rather than one-time discovery. Climate variability introduces uncertainty. Ice cover duration changes gradually. Surface temperatures trend upwards slightly. Wind patterns shift. These factors interact with ecological and geological processes in ways that cannot be predicted perfectly. Human influence continues to test resilience. Tourism grows. Infrastructure expands. Conservation policy evolves. Pollution monitoring improves, recovery from past industrial impacts progresses, but no system as large and interconnected as Baikal can be sealed entirely from external pressure. Technology extends our reach further than ever before. Sonar maps deeper slopes, autonomous vehicles operate under ice, genetic sequencing identifies organisms invisible to earlier microscopes, computational models simulate water circulation patterns across seasons, and still, these tools illuminate portions, not totality. There is also the matter of timescale. Baikal is approximately 25 million years old. Modern scientific study of the lake spans little more than a century in concentrated form. Even with advanced instrumentation, we are observing a system whose full rhythm extends far beyond human lifespans. This mismatch between natural duration and human study period ensures that some processes remain partially understood. Sediment layers preserve evidence of past climate cycles we're still deciphering. Tectonic widening continues at millimeters per year, imperceptible in daily experience but profound over millennia. Even clarity can conceal. The lake's water is famously transparent near the surface, yet transparency in appearance does not equate to transparency in understanding. Chemical gradients, microbial interactions, and deep ecological networks operate invisibly. The phrase keeps its secrets does not imply deliberate concealment. It reflects the reality that in systems of sufficient scale and dynamism, complete comprehension becomes an asymptote rather than an endpoint. Knowledge approaches fullness but never entirely reaches it. Scientific humility grows naturally from that recognition. Researchers working at Baikal understand that each dataset contributes to a broader picture, yet no single study defines the whole. Collaboration across disciplines becomes essential because geology, chemistry, biology, and climatology intersect continuously within the basin. Cultural perspectives reinforce this humility. Indigenous traditions emphasizing respect rather than domination align unexpectedly well with modern ecological science. Both recognize that interaction with such a system requires care. Conservation strategy also reflects the lake's complexity. Protecting Baikal means safeguarding not only visible shoreline and iconic species, but also deep water processes, sediment stability, and long-term climate resilience. Policy must anticipate uncertainty rather than react solely to confirmed damage. For visitors standing on the shore, the lake may appear calm and fully present. Mountains reflect on the surface. Wind patterns trace across the water. Ice glows blue in winter sunlight. Nothing about that view immediately suggests limits. Yet beneath that view lies more than 1,600 meters of water, kilometers of sediment, fault lines slowly separating continental crust, microbial networks operating beyond sight, and seasonal processes cycling quietly year after year. We can descend with submersibles. We can drill sediment cores. We can deploy monitoring arrays. We can analyze chemical signatures down to trace concentrations. We can model circulation patterns with increasing precision. Each effort reveals more detail. And still, Baikal remains dynamic. Conditions next year will not match conditions exactly this year. Geological stress will shift slightly. Ice may form earlier or later. Species distributions may adjust subtly. Perhaps that is the real reason we cannot truly explore Lake Baikal in the absolute sense. Not because it is inaccessible, but because it is alive in geological and ecological terms. Exploration assumes a stable object to be known completely. Baikal offers instead a moving system. That does not diminish the value of study. It deepens it. Continuous observation becomes not a failure to finish, but an acknowledgement that understanding must keep pace with change. So the lake keeps its secrets not through darkness alone, nor through depth alone, nor through scale alone, but through the accumulation of all those factors operating together. Each descent answers questions. Each winter brings new data. Each generation refines models. And the water remains, older than most landscapes on Earth, holding within it records of climates long gone, species found nowhere else, tectonic movement still unfolding, inviting exploration, accepting measurement, and continuing quietly beyond the edge of what any single era can completely grasp.